All right, welcome back. So our next speaker is Allan. Allan MacDonald from Beauty, Texas. Multi-moiré TND materials. I'll show you him.
Okay, very good. Okay, so it's delightful to be here. The first time I heard the name Boris Schlossky was in fall of 1982. I was lucky enough to spend a year with Morris Rice at ATA Zurich when he just left Bell Labs. And as his first academic exercise, he gave a special topics course on all of the interesting stuff going on at that time on, disorder, weak localization, and so on. And the first paper he told us about was this one. I remember, sometimes we're all, I think, in this room nerdy enough to have the feeling of during a lecture, the penny drops and the sense of pleasure of learning something new. So I can remember that from Morris's lectures. And so I like this paper so much that I copied it. And little did I know then that I would have opportunities in the future to meet and interact with Boris in person. Very often here, either in this lecture hall or outside of this lecture hall or over in the graduate hotel lecture spaces in the old days. And so it's all been a lot of fun talking about quantum Hall edge dates and STO2 digs and so on. But I want to specifically mention Boris, one thing I'm particularly grateful for. Sometime, I don't know how long ago, I had a bout of sciatica when I was at a conference dinner at this Adriatic at the Institute for Theoretical Physics in Trieste. And after dinner, I was sitting on the corner of the street, unable to move. And this man lifted me up, dragged me back to this guest house. Otherwise, I'd still be sitting on a street corner. Yes. So, Morris, thank you for many, many things, including that evening. Okay.
I remember that.
So I'm going to tell a story that's motivated by the recent discovery of the fractional quantum Hall effect without a magnetic field in a particular type of moiré material. As most of you know, moiré materials are a trick for making artificial crystals on a convenient length scale with lattice constants around 10 nanometers or so that you can change the number of electrons per atom by big enough numbers with electrical gates. And this is a particular type of moiré material, a moiré, based on a moiré pattern of two layers of the transition metal dichalcogenide, two-dimensional semiconductor molybdenum ditelluride that are twisted with respect to each other. And in this moiré material recently, it's been discovered that the fractional quantum Hall effect occurs without any magnetic field. So this was originally seen in labs of Xiaodong Zhu and Climac and Jishan, and has now been confirmed in a number of different laboratories around the world. So there's no doubt that it's real. And so my story is going to be trying to at least partially answer the question, why does this happen? And so my talk is drawn from the work of many people, and I particularly like to mention Benchen Wu, who was a student in my groups a few years ago and is now a professor at Wuhan University. And he was really the first person who understood that this particular type of moiré material was special. And I'll mention the others as I go along. Okay. So the title of this workshop is Long Range Interactions and Disorder. And for the fractional churn insulator, both long range interactions and disorder are important. So I want to first mention something, an incorrect theory of superconductivity proposed by Fritz London and related work by Werner Heisenberg back in the 1940s, but people didn't know what was going on. And this is an equation from one of London's papers. I think we all recognize the Fourier transform of the Coulomb interaction in 3 dimensions, which looks strange to me after all these years. So the point, the argument they make in this paper is basically this. If I have some electrons in momentum space, they want to form a compact structure. They want to get as close to each other as possible, consistent with the Pauli exclusion principle, in order to have the momentum differences of the occupied states to be small, and therefore in order to have a large exchange energy. And they call this condensation in momentum space, and they argued incorrectly that condensation in momentum space can explain superconductivity. Notice that this argument depends very much on the fact that the Coulomb interaction is large at small distances in momentum space, which is the long range interaction property. And so momentum space condensation is in fact something that's common in moiré materials and common in 2-dimensional materials generally. Here I'm showing you pictures of the band structure of the 2 best understood 2D materials, graphene multi-layers based on this platform, and 2D semiconductors, TNDs, or multi-layers based on this platform. In both cases, the low energy states, the states that are close to the Fermi level, typical situations, are located near 2 inequivalent Bruaz corners of the triangular lattice Bruaz zone, called here K and K prime, related to each other by time reversal symmetry. And so what happens in all of these systems where if I put in carriers, for example, holes in the valence band of semiconductors, the case we'll be talking about, they should go into both valleys. But very often, if the bands are flat enough, single particle energies are small enough, they prefer to condense in momentum space to occupy only one of the 2 valleys. And that's the starting point for moiré materials. In fact, there is a somewhat subtler, somewhat more subtle consequence of this exchange in momentum space that operates even within a single valley. What I'm showing you here is a depiction of the energy bands of, I think this is bilayer graphene. Where the wave functions are linear combinations, as in the case of the moiré systems I'll be talking about, linear combinations of components in 2 different valleys, and the blue arrows represent the X and Y components of this layer pseudospin. The direction of these arrows represents the phase difference between the components in the two layers, and the magnitude represents the magnitude of the x and y components of the layer pseudospin as a function of momentum. So what this shows is something that any of you who've been following properties of graphene systems know, is that the phase difference, in this case between layers, winds with the direction of momentum. So that winding number is the topological property. And this pole in the middle here is saying that the exchange energies don't want the momentum direction to change rapidly in momentum space. They'd rather carve out a vortex core here in which they are localized in one layer or the other, in order to minimize exchange energy. So that also happens in these systems even after they're valley polarized. And that means that a layer state as a function of momentum covers area on the block sphere, and that means that that there's non-zero Berry curvatures. So non-zero Berry curvatures do often occur spontaneously, are often spontaneously present in the valley polarized, valley projected bands of the system. But where they're not, interactions will often create bands that have non-zero Berry curvature, even without this. So the physics that's behind spontaneous valley polarization, which we can also call orbital ferromagnetism, it's the way orbital ferromagnetism occurs in these systems, and also with the fact that these orbitally polarized states have non-zero Hall conductivities, is also related to the long range of Coulomb interaction. I'm not going to go through this slide in detail, but what it shows for bilayer graphene is that the ground states at neutrality are in one of these two valleys I mentioned, and there are also spin states. So there are 4 of these states, 4 so-called flavors. Each of these flavors tends to carry a Hall conductivity, but the actual ground state of this system is, we know from experiment, is one in which the total Hall conductivity is 0. So you don't see a quantum anomalous Hall effect, but you don't need to apply much of a magnetic field to get in bilayer graphene to get a quantum Hall effect. It's almost there at 0 field. Okay, so in graphene, we have these 4 valleys. We can change the wave functions a little bit by what I was trying to describe as spontaneous valley polarization. But basically, the bands in there are no bands in momentum space. There's only special point is neutrality, and so all of this becomes much richer in moiré materials, as I'll explain, where you have all of the same ingredients, but in addition you have bands in a mini Brouin zone associated with the moiré pattern. Okay. So I'm going to talk about fractional quantum Hall effect, also called fractional churn insulator, in TMD moiré material. There had prior to these more recent experiments, there had been a lot of work on heterobilayer TMD moiré materials. This is an example from the work of laboratory of Phonons, who will speak later. And, you know, what it shows, these are actually reflectance, contrast measurements. So taking advantage of the fact that you can probe these systems optically. But the main thing to notice here is the dark, or these features that occur if you look at the label on the top at fractional filling factors and are interpreted as evidence for gaps being present in the system, in the charge system. So in this case, at fractional band fillings, you can get energy gaps appearing due to interactions. So energy gap in a many-body sense is, you know, difference in energy, the energy to add an electron and the energy to remove an electron, or a jump in the chemical potential of the system. So jumps in the chemical potential of these artificial crystals at fractional fillings of a band are were seen from the beginning. And and it's, you know, if you make a lattice model of these systems, for example, there's one favorable position in this case in each Moiré unit cell for the carriers, holes actually to sit. So the holes sit on lattice sites, and so it's easy to understand that you can place holes on lattice sites that are farther away if the band filling factor is smaller, and that this evolution with band filling factor does not occur spontaneously. I mainly want to you know, say what I'm trying to say, what you need to prove to say microscopically that a system is a fractional churn insulator. What property is it of you know, of a band Hamiltonian that makes a fractional churn insulator? So this is a set of arguments connected about the quantum Hall effect. You know, these things that are said in this 3 steps in this cartoon are said in many similar ways. But what I want to say is the all the phenomenology of the quantum Hall effect occurs when I have a gap, a jump in the chemical potential, at a density that depends on magnetic field. If you have a gap at a density that depends on magnetic field, that means you have orbital magnetization that depends on chemical potential produced by circulating edge currents, and that's really what's measured in most quantum Hall transport measurements, which measure a conductance. They're really just measuring how much more edge current flows. It's almost an equilibrium property of the system for a slight change in chemical potential. And so the question then, if we have a band system, is why, this should say, why should the density at which the chemical potential jumps depend on magnetic field? That's what you need to prove to understand microscopically when we say system is a fractional churn insulator. So I'm going to try and give you one answer to that question. Why are there fractional churn insulators in TMD homobilayer moirés? And so in the first place, what happens in this system is a consequence of its stacking. It's a serendipitous consequence of this stacking pattern. So this is a very nice illustration from a review article by Phi and G, and the case we're interested in is what is called here AA stacking. I think you all know that the transition metal dichalcogenides are three triangular lattice, stacked triangular lattices with a metal triangular lattice in the middle and chalcogen triangular lattices on the outside layers. And if you look from above, these ones will form together the two systems will form a honeycomb lattice. And so, as you can see here, when the two layers are stacked one on top of each other, and you make a moiré pattern. So moiré pattern here is made by twists, but a moiré pattern is really just a slow spatial change, regular spatial change, periodic spatial change in the stacking arrangement between the layers. So locally, when you twist the layer, say the top layer, locally you're just moving the top layer relative to the bottom layer. And in this particular case, you can easily see that if I move the metal atom in the top layer to the right, it'll be above a chalcogen below. And in these TND semiconductors, the states at the top of the valence band are metal states, transition metal states. Those transition metals see the chalcogen sites in the layer below as negative charge, which is repulsive for electrons and attractive for holes. So when you have NX stacking, then the metal atoms want to be polarized in the top layer. If you drag this metal atom in the same direction or the opposite direction, the metal atom below will be below the chalcogen above, and then the electrons on the metal atoms want to be in the layer below. So there's a spatial pattern in this moiré system in the layer dependence of the Hamiltonian. That's behind everything. The example I gave you before, Dirac-based or graphene-based systems, we can understand the origin of the topology from momentum space. But in these semiconductors, there's no band crossing or anything in momentum space. There's a single lonely band, innocent lonely band at the top of the valence bands in these materials. And so any topology has to come in a bilayer from the fact that I have two layers, and something interesting is happening with the layer degree of freedom. Right? So so by the way, so I'm going to imagine for most of my talk that the world of AA homobilayer moiré materials, TMDs, is the same, identical to the world of a set of 3-parameter Hamiltonians, in which you have a kinetic energy in a B for bottom layer, T for top layer here. You have a potential in the bottom layer that's different from the potential in the top layer, as I've been explaining. So that's a layer dependence of the potential, and you have tunneling between the layers. And if you assume that these position-dependent functions vary smoothly and use the symmetries of the problem, you can describe all of this by a 3-parameter model, which depends on the size of these potential variations I was describing and the strength of the tunnel, and also whether the potential variations, where the potential variations make extrema of the potential. But I told you the extrema of potential are always at these MX and XM positions. So this parameter psi, which determines where the extrema of the potential are located, is more or less always the same position. And so I'm going to be referring later to basically the strength of this potential and the strength of the tunnel, which is restricted to one parameter from symmetry, if you assume it's smooth. Okay, so this is the thing that Feng-Cheng Wu, a property that Feng-Cheng Wu observed. The Hamiltonian of this system, if you look at the layer dependence terms of the Hamiltonian and view them as an effective magnetic field that acts on a layer pseudospin degree of freedom, they have a topological character in real space. They have these metal on chalcogen positions, chalcogen on metal. And if you look at what's going on in the rest of the unit cell, you can see that this covers entire block sphere of two layer states, a block sphere of two level states, two levels being the top layer and the bottom layer, once in every unit cell of the moiré pattern. So that's the nature of the periodic Hamiltonian in this system, that it has this skyrmion structure in the field that acts on the layer pseudospin. So here I've made this a little bit more explicit, and I'm going to see what I'm going to say next. Okay. Yeah, so I'm going to say that these in these systems, under the right circumstances, the poles behave like particles in a magnetic field, which explains why they have the same quantum Hall effect and fractional quantum Hall effect is in a magnetic field. And so first I'm going to say that, and in a hand wavy way, and then I'll say it in a mathematical way. So what I'm drawing here is a Berry phase associated with the adiabatic evolution of a what we call electron moving through this moiré pattern. And the moiré pattern, of course, is many lattice constants in period. And assuming that the two-layer state at each unit of position adiabatically follows the direction of this pseudospin field, which comes partly from tunneling and partly from the potential difference. And we know that this is the first example of Berry phases, that if you look at the adiabatic evolution of the spin-a-half particle, and if you cover the entire block sphere of states, as we do here in one unit cell, because we have skyrmions in real space, then you get a phase of 2 pi. And so this 2 pi Berry phase in every unit cell can be mapped to an Aronoff-Bohm phase from an effective magnetic field. And mathematically, you can get the same result if you make a transformation, position-dependent transformation, so that the layer pseudospin quantization direction is at every position lined up with the magnetic field. That will follow the evolution of the state. And if you project the Hamiltonian onto that state, you lose the spinor structure associated with layer. And what you pick up is, as I suggested a moment ago, an effective magnetic field. The magnetic field is not uniform. At every position, it's determined by how much of the unit cell area you're sweeping out, or block sphere area you're sweeping out per unit area in real space. In addition, you get the energy. This delta tilde of R is simply the energy, local energy of an electron aligned with the pseudospin field. Question?
Is the vector potential is also a matrix, two matrix? Or?
Yes. Yeah. So this in this approximation, we project to the state that's aligned with the magnetic field. Right, so you lose the matrix structure in that approximation. Call it adiabatic approximation. Go ahead.
Is it gauge invariant?
Uh, let me say yes. Okay. Okay. Yeah. Let me mention one property, a numerical property of the models I was talking about that was noticed in the group of Liang Fu several years ago. And you know, normally in these moiré materials, as you change the twist angle, that means the period of the moiré gets smaller, and the distance from one low energy position from the electrons to another gets smaller, and the bands get broader. The blue line here is bandwidth. And this is bandwidth as a function of twist angle or inverse Moiré lattice constant. And the general trend of increasing with twist angle is interrupted at a certain point. And that is, I'm going to explain what's going on at that point, okay? So the form of the Hamiltonian that we got in this adiabatic approximation is, you know, just a particle with a kinetic energy and some kind of potential. And I can rewrite this, even if the magnetic field is not constant, I can rewrite this as some sort of combination of raising and lowering operators. I'll come back to in just a moment. But basically with a 0 point kinetic energy and some sort of potential energy. And you know what Aronoff-Kasher noticed in this paper from 1979 was that for a normal electron gas with a G factor of 2, you get this potential is just the Zeeman energy. And so what happens if you have electron gas with a G factor of 2, these two terms cancel exactly. And so what's going on in these Homobilayer systems is that under certain circumstances, these two terms cancel, not exactly, but exactly enough. Okay? And so you basically have these Aronoff-Kasher type wave functions. And here's a numerical sort of demonstration of that property. Here I've defined the function u of r, which is all of the terms that have to cancel in order to get this same property that you get in a 2D electron gas with G equal 2. So in this G equal 2 system, I should have emphasized more. You know, you get basically the lowest Landau level is there, even if the magnetic field is not constant. And so what I'm going to argue is that for these low kinetic energy wave functions, it's not this, you know, in our case, the two things that need to cancel are different functions of position. There's no way to get them to cancel identically. Instead, you can get them to sort of cancel on average. And in these lowest kinetic energy wave functions, the wave functions are smooth. So the argument is they don't see the rapid variations in this potential u of r. And so this is basically Fourier expanding U of R. It turns out this function has honeycomb lattice symmetry. So there's one real number for every shell of momentum space. And you can see that if the first shell, which are the most smoothly varying components in this residual potential, when it vanished, then nearly independent of higher Fourier components, you get Landau level like results. You get Landau level like results. The bandwidth goes to 0, just what I showed you, and also there's a property that you can relate to quantum geometry that I won't talk about, which is basically a measure when this quantity is equal to 1. That means the wave functions look like those of Landau levels, in particular their analytic wave functions. This is just showing you what the form factors are associated with the smoothness of the wave function and their ability to respond to things that vary rapidly in space based on a calculation of actual Landau levels. And this sort of illustrates the point that it doesn't matter what's going on. I don't have time to explain this, but let me just say that there's a prediction that comes from all this, and that is to get this cancellation to occur, then you need the 0 point kinetic energy, which turns out is big where the wave functions are changing rapidly, which is out near the corner of this unit cell, which contains the mx and xm points, and to be roughly the same size as the tunneling between the layers, which is biggest at the mm points. And so the prediction is that if you press on this system, put the layers close together, all this topological stuff will go away. And because you won't have these two things being roughly the same order of magnitude. And so now I have 5 minutes. Is that right, Alex? Run.
Well, 2.
Yeah. Okay. So let me attempt to say this. So I was trying to convince you before that it's really strange to get a fractional Chern insulator. If you think about a lattice model, for example, if you have electrons sitting on lattice sites and you take the usual strong interaction limit, then the electrons don't know about the magnetic field at all. All of the gaps have to be these Wigner crystal type gaps that occur at a density that's a certain fraction of the band filling, and the fraction at which it occurs doesn't change with magnetic field. So the electrons staying each away from each other on lattice sites is the characteristic property of Wigner crystals or Mott insulators and so on. We know from what we know about the fractional quantum Hall effect that the characteristic property is making wave functions where the zeros of the wave function are located at the positions of the particles. And if you add a magnetic field, you've got more zeros in the wave function. And that's why you can change the density at which you can, let's say, have low energy states. And this property of, that the low energy many body states are connected more to zeros than to, being localized on certain lattice sites, is nicely captured, as Klaus mentioned this morning, this symmetric gauge that everybody wants to use, where the wave functions are just analytic wave functions, so they have nice zero properties. None of this changes when you have a non-uniform magnetic field. It turns out that the wave functions are powers of coordinate z to the m times a common function, And the Laplacian of that function is the effective magnetic field, whatever it is. It changes when you add the external magnetic field. And so the effective magnetic field is, if you view this wave function squared as a distribution function like a plasma distribution function, then you can see that the position-dependent effective magnetic field is basically the charge density, acts like the charge density distribution for this plasma. And the yeah, so this is basically Bob Laughlin's plasma analogy for the fractional quantum Hall effect, showing that, you know, states with 3 zeros at the position of every other particle, which are low energy states, actually those wave functions are uniformly distributed in space. They have uniform charge density. All of that generalizes to this case, except uniform doesn't mean uniform, it just means same charge in every unit cell. There's no translational symmetry breaking. And if you add a magnetic field, then in this plasma analogy where the total particle charge has to match the total background charge, then if you add a magnetic field, you're just adding a little bit of background charge density. And that means you can have larger particle density. Okay. And so I'm not going to tell you that. Let me just say this, that you can, there is a lattice model for these, which captures the same physics with just 3 atoms per unit cell. And that's what it looks like in real space. You can ask me about this later if you like. But when I spend my, when I toss and turn at night, it's trying to find a version of this lattice model which has exact 0 energy states. So I hope I can create some insomnia for somebody else as well. So let me just go to there. Okay. So yeah, thanks very much.
We have time for one quick question, please. Yes, Misha.
So what's exactly the condition for the band structure to have this property? This vertexability, or how you call it, flatness?
Well, there's a quantum geometry condition, right? But I'm sort of like,
What is this condition? What is quantum geometry?
what is it? So, it seems kind of like artificial. Why should you have that condition? But what that condition really says is the wave functions are lambda level. And the effective Hamiltonian is like that, is actually equivalent to that of an Aronoff-Kasher system in some periodic effective magnetic field. If you're going to ask me mathematically, it's very unintuitive. I don't have, yeah. So, yeah, I probably can't say anything useful.
All right, we'll have time during lunch break.
Yeah.
Coffee break. Let's thank Allan again. All right, so our next speaker also has some experience talking in this room. Once or twice.
Oh, in this room, yes. In other rooms. Oh.
All right, so our next speaker is Leonid Glazman from Yale. He will tell us about seeing phonons with at least microscope. I'll show you 10 minutes.
Let's everybody here again. So I'll be talking about ongoing work. So some of the kind of new loose ends, and it's on the side it's the work that is done with Allan from Berlin and MacDonald, Spain, and experimental science Allan group. Glazman, one of his students actually is also doing very good actually in Syria. The initial motivation for us was to assess the role of phonons in DPG distant by layer superconductivity. And another motivation was that Chiral came up with this very interesting tool, quantum physics Microscope, which I'll tell you about a few years ago. So what they'll do, I'll tell you a bit about the general theory of frequent tunneling PGM for radiation, which allows to consider kind of on the same footing elastic and inelastic tunneling, and it allowed us to kind of to redo essentially what they did in experimental paper with elastic tunneling, but also kind of progress a bit towards understanding of the phonon-assisted tunneling and the microphone characteristic, which is the main goal of this line of research. You can make sense of some of the data. So, interesting thing about Fourier patterns and this polarography is that it creates puzzles that rate higher than getting results. So there is a backlogging of result things, and one of them is actually superconductivity, I believe. It was seen right away in the first groundbreaking experiments of Pablo. MIT, and these experiments kind of keep happening. What does the glue? Not entirely clear. So the origin of superconductivity remains elusive. And Phonons is a natural suspect. Now, in early days, which is only 5 years ago, Andrea Young measured the temperature dependence of resistivity. It's conspicuously linear, and there were a large number of theory papers. Some had several in various directions, but then the directions are strong and somehow they're low. It's Phonons. Field origin is not clear. Now, kind of to poke closer into the phonon interaction. Well, there is another tool which is called angular result derivation ARPAS. And there is a very recent preprint. I think that earlier Rottenberg has the leading senior author there. So basically, ARPAS is you yank out an electron with a photon from the solid, and what they saw is kind of satellites separated by a presumably phonon frequency, but it's EDC, it's energy distribution curve. There is no momentum resolution at all. So in kind of momentum space, it looks like some nebulous clouds corresponding to the processes of inelastic extraction of electron with simultaneous emission of an optical phonon. There was almost immediately a series, but I've heard that authors start to disbelieving it themselves, and usually predictions of delta or TC is notoriously difficult. So let's maybe not focus on that. So now, now about this new experimental tool, which actually heard first in Chiral's talk, and it's kind of mesmerizing. So basically, it's like spherical microscope STM, but instead of the needle, there's kind of a flattish thing covered with under glass crystal, which for instance was just graphene. And what they can do is basically scan surface and twist the cantilever, controllably with pieces, and basically measure position and simultaneously and angle and simultaneously measuring the tunnel current. So because it's flat and it's a substantial piece of surface or flake, basically its momentum result, or what momentum we'll talk about this. So it's a little bit like Arcus, but at lower energies and with much more control. Now, so for elastic tunneling, if you look at small biases, because of the very sharp rays of Dirac spectrum around KK prime points, which is just in the previous, basically only small twist angles produce a large current because you have to overlap occupied state with an empty state, and this empty state just go almost vertically, and a small angle, small rotation angle that corresponds to some change in the momentum between the two K points in top and bottom layer will create large change of energy. So it's only small twists that produce current. And that what was seen in an experiment. I'll dwell on details of the structure a bit later, but it's relatively small angles, it's degrees. Now, here is a curve in a bigger range of angles, and there are these additional peaks, and that's because momentum is different from quasi momentum. So of course, tunneling preserves momentum, but not quasi momentum. So quasi momentum is conserved up to the inverse lattice period and reciprocal lattice period, and basically these two peaks correspond to adding a reciprocal lattice period to the momentum of tunneling electron. And there are sharp peaks. Now, that's for elastic tunneling. So, and this is the IDV, and what started our collaboration is that if they look more carefully in the second derivative, there are some lines that have much lower slopes in voltage bias versus angle plot. And these lines most probably are Phonons. Well, they are Phonons. I'll tell a bit later. Now, so why is there low, and why actually this is somewhat exciting? Well, the thing is that the velocity of direct electron is high, and if you have, say, a large twist, to tunnel elastically, you have to apply an enormously large bias. Suppose you apply only small bias, then you need a phonon to go basically from K point to K point in another layer, and the solar frequency is much smaller than the respective energy of electron if I would give this entire momentum to electron. So basically, electron takes only a small portion of momentum, and the same gets a pretty high resolution in momentum for phonons, and the energy is controlled by the bias. So that's kind of a natural tool to investigate the spectrum of phonons. And unlike Arcus that have shown, basically the energy feature, the current bias characteristic features associated with phonons are far, far away. They're very well separated from the elastic ones. So that makes things much better. So that's number one. Now, what was pleasing for me personally is number two. So again, because of this condition, basically the involved electron momenta are small, and there this machinery that I had a chance to do recently of Allan, MacDonald, and Induced works, and one can just do a lot using essentially a field theory description for electrons, wave packets, and not slaving with the tight binding calculations every time. So now, what is the setup for calculation? So if you look at tunneling, so the first term, material term is just tunnel Hamiltonian, and then there are two terms that should account to look at least at single phonon emission processes. This last one, this first one of the two is conventional. So it just, the intra, yeah. So intra is within the layer. So basically, electron tunnels into another layer, and there it emits a phonon and ends on the mesh shell, on the real electron energy state. Now there is another guy, H inter, And this is modulation of tunneling by phonons. So basically, I can shift one lattice respect to another, and it will produce change of the tunnel Hamiltonian. And it also leads to the effective electron-phonon interaction. So now let's focus first on the tunneling. And if I look at just elastic processes, then, okay, it's a conventional group formula for, sorry, it's the conventional form of the tunnel Hamiltonian. It basically vertical tunneling, and W is the energy scale for the tunneling matrix element. And this is just for dimensions to have them right. These are creation negation operators for electrons in the two layers. Now, if I look on the elastic tunneling, I can use this Hamiltonian to derive the proper current. Now, this intra term I already said, but the second the also be here in inter. So inter basically tells that there is a change of the Hamiltonian when I shift the layers respect to each other, and this is also kind of important that we have separate derivatives of the Hamiltonian respect to the top and bottom displacements. That means that actually this term is not entirely translationally invariant. So basically, shift of one layer respect to another, even this small wave vector, would matter. And this is different because that will make this term more sensitive to acoustic phonons that usually are not that important in electron-phonon interaction. So getting back to the elastic tunneling, we can write down elastic current just by from the Gould rule, density of the states, distribution functions, energy conservation, W squared. Then we know that because we want to eventually do spectroscopy of phonons, I would like to have Fermi circles as small as possible. So I would like to work near the neutrality point, and that allows me, at least for now, assumes that there is no screening. So basically, neutrality points, the density is small, and we neglect the creation of electric field by electrons and holes themselves. So in this case, I can relate chemical potential just to apply bias and a very simple calculation if I assume that there is no any momentum conservation. So if I just completely look at the case of incoherent elastic tunneling, images just made these layers very dirty, which is impossible, and there is no momentum conservation. Okay, so that will be the setting, and I just needed to introduce a characteristic scale for the conductance, tunneling conductance, and the scale is independent of this parameter lambda f because we need the spectrum cancels out, and it depends only on the conduct area, on the degeneracy, and again, this thing is just a characteristic of the junction and their spectrum. So I did it just as a scale because all the quantities that I will calculate, I will normalize to this incoherent G. Now, when screening is unimportant. Basically, when I apply bias and shift the Diracs to each other, okay, if there would be neutral particles, then I'll just populate one layer and populate another layer. But they're not neutral, they're charged, and therefore they counteract and create some say potential. So one can just write down the nonlinear screening, Thomas Fermi theory for this potential, and basically the condition to have negligible shift of Dirac points with respect to each other is the condition that Thomas Fermi wave vector times the distance between the layers, the product eventually is small. As I said, I was hit that when working this out, I recalled that I have read first about nonlinear screening from a popular in my kindergarten storybook. And it was just a side story, but master could explain. So now, that's very right. So now, if we want to so we had this incoherent tunneling just to set the scale, and now I would like to introduce back the momentum conservation. And again, one may try to use, at least for me, it was as well. It was good to use the intuition developed for the Landauer style formula. So imagine that you have just two strips on top of each other. This is our top and bottom graphene layers, and you can cast the current formula into the kind of Landauer style expression for the current, where T should be seen as a transmission coefficient. So now it's finite fit, so Kx is quantized and it's just modes. So we have a certain number of modes for given bits. And there is energy of the incoming particle or a wave. And in the tunneling, momentum Ky is conserved. And if you work out the details, then basically you find that this tunneling probability has this form with momentum conservation, as I said, and this Ky depends on the mode number, Kx, and energy. So this guy overall preserves the entire momentum. And as I said, we start with a wave here, and it propagates in this region of tunneling, and there is some probability that it ends in the opposite layer. So it starts blue and ends red. So, well, in principle, one can just, take this and print the handle. But it's possible to understand actually what's interesting about this setting. So basically, imagine I fix this angle which fixes the distance between electrons and raise bias. Now the states are full, but as long as they are not engaging the empty states, nothing happens. There is no current. And eventually, when chemical potential is high enough, then there is some region where the occupied states overlap with empty states in the bottom layer, and then current happens. And basically, the current is due to the states that are in some segment in momentum space, and the width of the segment depends on how far we are above the threshold that, at which these two circles just kiss each other. So the width of this segment grows a square root, well, obviously, with the increase of VB bias compared to the measured from the threshold value. And as a result, DIDV has a 1 over square root singularity at the threshold. And again, here even coefficients are right. So that's a threshold due to this band overlap. Now there is another interesting thing. So imagine that you start with this, okay, and you crank up chemical potential bias further. Then eventually the screening starts to be important, and this two direct points become shifted with respect to each other by some E5. Now I can keep increasing mu. It's better to first to reduce a little bit the twist angle. So let's do that. Okay, and I'm increasing mu, and eventually this blue cone just matches the direct cone. They nest each other, which means that there is an interval of energies where the electron velocities in layers are equal each other, and that means that tunneling becomes extremely strong. So basically, this is the point at which perturbation theory fails, and the signature of this failure is actually current, at least perturbatively completed, is diverging as 1 square root of the differences of the phi of the potentials for the two layers. So basically, this difference phi of B is the is a difference between the direct points at which the netting happens. So this is critical and this is above the critical. So basically, this leads to even a stronger feature in the current, and it's currently is believed, and it's already wasn't there, that it was paper that this blue sharper lines are the manifestations of the nesting. So with this machinery, we can now go and look at the Induced scattering, sorry, emission. So once again, I'm showing the estimates, but this Phonons becomes really hairy because one has to account for the polarizations, different modes, and there in which this MacDonald is very convenient because it abbreviates the electron part of calculation quite a bit. Let's again focus on this inter part, which I already split up once. This one. Basically, one can use the developed formulas, this Landau-like equations, to treat this part quite easily. Basically, it's slight extension of what I told. Here, I'm more careful and I'm writing at zero temperature tunneling, where I have calculated state at the top layer and empty state where electron lands. And this guy, the transmission coefficient, is actually a coefficient with emission of a phonon. Now, of course, because of finite Fermi circles, one can emit not a single phonon, but various phonons. But again, because of the difference, because of the high velocity of direct electrons, they spread in the vectors of a phonon is very small. So basically, even for acoustic phonon, as long as Q naught is large enough, this is negligible, and we can just lump together all the possible phonons into one frequency. This omega to 0, and basically this is estimate for the free factor, and this L, the 0-point motion, is the amplitude of 0-point motion in a given mode. So it depends on the frequency of the modus 1/√omega. So again, for acoustic modes, this L gets large because of small Q. And again, this point that I tried to make earlier, the translation invariance doesn't save you here because this motion is not translation invariant motion. It's motion of one layer to another, and that's why it's sensitive to long wavelengths as well. Now there are some interesting caveats. If you look at calculation, turns out actually that this process that I just explained, this motion, is effective for the transverse modes, but not for longitudinal modes. And the reason is that if you just work this out, the main term in the Hamiltonian comes from the shifts of the Bloch wave functions. And the Bloch wave function has a large modulation in the wave packet given by vector k measured from gamma point. So basically, this term has this k dot u terms in the as a factor. So the strongest effect is when the displacement, the Phonon displacement, is along the momentum of the electron measured from gamma point. Right? On the other hand, the wave vector of the emitted phonon should be equal to the difference between the two k points, direct points in the two layers. Okay? And it's just elementary geometry, right? So you can see that if angle theta is small, then it's essentially it's a transverse mode. Yep.
Also can be displaced out of plane in the direction of front.
Yes, right. So thanks. I suppressed it because of time. This is called so-called ZO and zero prime modes. ZO stands for this, and zero prime, if I remember, it stands for this. So it's different.
So they're less important than transverse.
They No, they are not less important. Okay, it's just a little bit, I wouldn't say a zoom. I'll show a table at the end where I mentioned them. But giving it in talk, it just I'll bore everybody to death, which I almost did, I think. But so basically, so far I'm just looking at this kind of motion in plane. But zero is there. I'll tell a little bit about it. Right. So now again, so the complementary part of the longitudinal, you just see this for small angles. It's suppressed due to the same factor. This is geometry, and for longitudinal U group is this way. It's not good. Now the second order process, it's just tedious. So you have to go through all the terms. One thing that I would like to mention when physics say is that when you do the scattering theory in higher order, you have this denominators coming from the virtual states. And the virtual state here is a state of an electron that is sort of at right momentum but wrong energy, right? So the right momentum means momentum that is given by the twist. So the smaller the twist, actually, the less wrong the energy. So the emitter becomes smaller and smaller when twist is small, and that leads to this 1/2 dependence for the optical modes, most longitudinal. So once again, the difference here is that in the intraterm acoustic phonons at small q are less dangerous because it's really the displacement of all atoms together in one layer, and translation invariance saves the day. But for optical modes, it's in one in every elementary cell, atoms move respect to each other, even at q equals 0. The motion is large, and therefore this energy deficit 1/q squared is not compensated by the powers of q that would be there for acoustic modes. So that's as far as I want to go with that. 4 minutes.
11 minutes.
Okay, so then basically, let me tell just the kind of outcome of the entire thing. So basically, these are just estimates. Okay? And the real theory also has dependencies of polarizations. Now, what allowed us to cast everything in such simple terms? So you see this GIDE is measured in this units of incoherent conductance, and these vectors don't contain any additional parameters except the Fermi wave vector, which depends on bias, and the zero-point motion amplitude. So there is I wouldn't say cheating, but there is a little bit of an assumption here, which is goes back to Anders' work on purified materials. So basically, we attribute the Phonon interaction in the layers to the bending of the bonds, and that corresponds to what is called, I think, the gauge phonons. Now, if one accounts also for the deformation potential, it's a bit different. It's also kind of stretching, and that I think is less important, but it's still not done. So if we do this just bending thing, then indeed, then everything can be expressed in terms of the same parameter, which is the tunnel matrix element, basically between the carbon atoms, and this is why the Phonon interaction is expressed also in terms of the bed parameters as an energy scale, and it cancels out except being present in G. But with the outer plane, This is an example where it doesn't work this way. Because the outer plane corresponds to changing distance between the layers. So the outer plane phonons is when I shift in vertical direction, say bottom layer towards the top layer. And this is really changing the length of the bond. So then there's additional parameter, which is a separate parameter itself. So that's basically all I know about this modes. Now, does it allow anything useful in terms of the interpretation of what they saw? So I mean, without theory input, they already took the Phonon spectra for the graphite insulated material. So what do you expect? So basically, the positions of the lines fit reasonably well to the proper modes in graphite. What is interesting and interesting detail that so first of all, the longitudinal acoustic mode is almost not seen. The dashed line is there, but with no contrast, and that bodes well with our conclusion that basically it's hard to couple to longitudinal one. Whereas the transverse acoustic mode is present, and it becomes more and more bright at small angles, which also corresponds to this 0-point motion scaling as 1/square cube. Now, another thing is that the optical modes also seem quite well, and also stronger towards the small angles, and that's maybe attributed also to this small energy deficit in the composite tunneling process, where the virtual state of electron is energy proportional to the wavelength cube. So that's what we I hope understand now, and that's where our knowledge ends at this point. So to conclude, so one thing is that I think that unlike ARPS, elastic processes are in the tunneling experiments are well separated from elastic ones, and that gives a hope to know way more about the quantitative information about the phonons. Most importantly, their interactions with electrons. Now, also, it's allows to resolve the effect of various polarizations, which is hardly possible in ARPS, and allows to probe acoustic moments. Now, how tell that actually, because of one interaction, they have very easy time to park this scanning tool at distance that corresponds to the natural distance for the say bilayer graphite, and therefore the tunneling actually corresponds to tunneling in a natural bilayer. Now, the thing is that, of course, if it's small angles, then just elastic tunneling is strong, and there is a bend moiré pattern. But if you twist, if twist angle is large, then the tunneling, electron tunneling, as I tried to explain this, is impossible because basically energies don't match. So you have the right distance, but you can see phonons, and this is the phonons at the right distance between the layers. So that's they hope would give some access to the intrinsic strength of the phonon interaction in twisted layers. Now, the limitation is that it's only for a relatively small span in phonon momentum, because you see, if you rotate, so the whole thing is C3, right? So 60 degrees is you're done. But there's also a mirror, so basically it's 30 degrees. So you scan only basically from 0 to 30, and then this part is a mirror image of this part. Well, it's not that mirror image that they just mirror it, it's experimental data. It's mirror. So another thing is that at very small twists, the elastic tunneling is so strong that they don't see much, and that's another limitation to this technique. Now, here's a notebook. And so reaching to look at whether this thing allowed also to look at the expressions in the broken symmetry phases. And actually, we're working Leonid way. A very good student of Allan. I was working on it, making some progress. Right. So yeah. So actually, I think that now it's time to get to the main point. I try to recall actually when I took course in course, and I strongly believe it was in '85. I think in May. It was in Odessa school.
Yeah, that's
On the beach.
of course.
I
I confirm.
Hopping connectivity, no hopping connectivity. And it's kind of a university of the source, right? So it's 39 years. You were taken over the time. They get 22 things. For example, Boris made the interdict hike. First hike, serious hike I had was with Boris in Aspen, and I can't click this image. So thanks, Boris. It's a privilege to go. That's our news.
Aspen is good.
We have time for questions. Yes, please. Just.
I still miss the point. You started from importance of this to superconductivity potentially, and the electron phonons strength
Yeah.
for that purpose. And what is the conclusion at the moment?
Well, first of all, there is no conclusion. The goal is to try to calculate what is called Eliasberg parameter, which is some integral of the electron phonon interaction over momentum
Does
space.
this help? Does this help?
Okay, so Hal hopes that it will help. Okay, so now they tell us that already using this formula, they extract the value of phonon interaction. Okay, so that's not my.
They say this helps. Okay.
They say it helps. Yeah.
Okay. More questions? Perfect. All right, so that's.
We deserve it.
Thank you. 5 minutes to the top of our.
Okay.
We went to 3 years ago in your work. I think one of them was by the University of this problem, it's like I was talking about the one man.
You're working.
I was
will ask you your comment.
That was
Relaxed now. I'm more balanced. Understand.
So, and the you shows.
Yeah. So I exactly. On the WhatsApp.
Yeah.
It's amazing. I think.
Meaning like if I were to, I would say 3 different kinds of account.
If you're lucky, then
Actually, you have
Bulk materials.
a 2D that can be exposed.
Yes, well, you know, this system ends up corresponding to a lattice. Some very specific properties. It would, it's, you know, it's a little bit like, you know, stuff like that, but the details are about, it's as if you had, let's imagine you had a triangular lattice or a honeycomb, okay, with S orbitals, honeycombs, and then you have P orbitals. of the honeycomb plaquette. So that's what the three elements are. So that would be good. So yeah, so the model ends up being side binding model. Ends up being you have a honeycomb lattice but the electrons actually and that honeycomb lattice is formed from the X and N side, right? But the an important tunneling maybe tunnel via another
Yeah. Run it on the background.
In the middle, so that's triangular lattice.
The Bradley lattice is triangular lattice. You had a honeycomb, you had two sites, right?
Yeah,
But in fact, you have three.
yes.
So all the honeycomb vertices, let's say plus the middle. That's what the three are.
Only the middle disappear, the others.
Yeah, yeah.
Actually, I am playing this bad structure. So there is S and T as a function of twist and roll the distance. I'm saying, so I'm playing with the type of models, considering three bands, three orbitals.
Three orbitals.
Two orbitals on honeycomb lattice.
Yeah.
One orbital on triangular lattice.
Yeah.
So the triangular lattice is in the center of the honeycomb.
Yeah, yeah, so that's the right one.
But I think this simple three band model is not fully
Unless you put it very long topic.
right.
So what is better? And nevertheless, I'm hoping that, I've been trying to find the exact solution, some interaction on this simple three-band model.
Yeah, so I think.
Not that I think it's quantitative.
15 minutes, but it's,
Yeah, sure.
Yeah.
you know, it's through the code.
I mean,
So you can go to.
Yeah, just see if you can get something like, lots of.
This is opposite to the camera.
No,
Analog, lots of exactly.
Yeah.
From 1/3 of the length.
So first on the other side of the.
Yeah.
Do you have any requirement on the exchange coupling strength? Or as long as they are like two S.
Okay, then I will see the.
And P of in the center, independent of exchange coupling, always.
What do you mean by exchange?
Meaning like the way I think about this kind of model, like of course, right, there's I mean, what orbitals they matter, but the strength of the hopping term between the adjacent.
Yeah. So you
Shouldn't
mean,
that-
you mean the hopping term?
Yeah. Shouldn't that matter as well? Does that needs to be tweaked for?
It does, certainly you can. To get the minimum. Probably the ratio between different hopping processes is important.
Actually, I talked to this one.
Yeah.
2 days ago. And he said it's T2. Relaxation is big, and that is.
Yeah.
So that makes. Different.
Yeah, that's probably true. The that the relaxation is more important than the.
Yes,
Yeah.
so that's the relaxation.
But so.
That.
Yes, and yeah, so we've looked at some pieces of that, but mostly we're assuming that
It's not.
it just changes the parameters of the model.
Quantitative.
Yeah. In other words.
But your theory predict that WS2 is using the.
very original functions.
Well, Funches paper, that
Okay.
paper, the originally submitted version of it was for tungsten. And then the referee said that in tungsten diselenide, the valence band maximum would be gamma. So, so then we changed it to molybdenum ditelluride. But, yeah, but it seems it works better in molybdenum ditelluride.
Yeah.
That's a quantitative issue, which is important to understand, but, you know. And
Yeah, so the reason I ask about this, like this hopping term is like, if that's only necessary for tuning it to be perfect, then can I imagine if I, for example, stack a honeycomb material, right? Like, for example, something simple graphene with just the one atom, on top of some triangular atoms, A/B stacking, right? So, but if the
Yeah.
second material has many p orbitals,
you know, I think the fact that there are two bands of graphene it changes things completely. So, and of course, yes, I'm not sure.
I mean, in general, maybe other material. Like
Yeah,
this,
yeah. Might be some other.
So it doesn't have to be just within one material, right? Like,
Yeah. Well, you know, usually it has to be within similar materials, right? Because the lattice constants need to be similar.
yeah, exactly.
Together. So,
Yeah.
okay,
I have a one.
Yeah.
related to-
Thank you.
talk
yeah, yeah,
about
nice to meet,
material.
nice to meet you.
Nice to
You
meet
see,
you.
you're here now, right?
I'm here now. I'm here as of a few years ago, actually.
Yeah,
Yeah.
You
We
came-
first met when we first met when I were just started, yeah, like a few years
yes,
ago.
okay,
Yeah, then nice talking to you. Yeah. So this twisting business is really getting very, very.
Has not stopping yet, thanks to you guys.
Thanks to you starting this video.
Yeah, that's the way tonight's matter of physics works, right? There has to be back and forth.
Yeah, I mean, especially glad to see there's more work, more like this beautiful work, like there's more.
No, that, yeah.
Yeah.
Of course, this there are still many things that were Vietnam.
I talked to him once, he said he would be.
Like in the topic, just to try. Right?
You know, as
Weeks went by and he.
Anya said in this talk, we're accumulating questions faster than answers.
So it's like when you have to.
Experiment.
So let me,
I still have
give me
a
a week.
question regarding those TMG materials. What makes MOT2 so special for? I mean, is this anomalous Phonon effect expected in other materials like twisted MS2 or?
Yeah, you know, generally speaking, something similar can occur in any TMG homobilayer. In some of them, the top of the valence band is at a different point in Pruitt zone. So then the physics would be different.
Okay,
So
so
those are so-called gamma valley systems. Right. But in principle, you know, there's not so much experimental activity, but tungsten diselenide can be similar because its valence band maximum bilayers is also at the K point. And I don't think the theoretical understanding is, you know, is good enough for theoretically to say, to predict the differences.
I see.
Yeah.
Okay. And what role does something like this relaxation play in those systems?
It definitely plays an important quantitative role.
So are there any implications of that?
You know, for mostly what everybody's doing so far is they, you know, I said we had a 3-parameter model like for these bilayers. So just changes the parameters.
Oh, I see.
Yeah.
But overall, the topology remains the same, so.
Yeah, so there's a certain way in this 3-parameter space, there's a region where you have topological states. And in principle, you can move in or out of that region, different materials. Yeah,
Okay, thank you.
yeah.
I was about to
So-
ask. ask one final question about, in the context of this twisted triangle, then I get alternate, with small twist angle with relaxation. I sometimes get AAA stacking order.
You're talking about graphene.
Graphing,
Yeah.
or in general, it could be
Yeah.
AAA, ABA, ABC. In some certain cases, they sort of, can I consider which of these stacking domains really large for them? Like,
Yeah.
is there any way that we can tune a system like this
So-
into
Yeah,
into a model that is similar to what you have been thinking? Maybe two of these domains are. I don't know whether it's right to think about to call it S orbital or P orbital. I'm just
Yeah.
thinking like whether, like this model that you are showing in general, right? Not only describe just not only describe this special type of lattice, but more generally, like moiré or super moiré.
yeah, I think I understand your question,
Mm.
so. Yeah, so, you know, one point is this, that. When you think about making moiré patterns. Then, you have some artificial periodicity. But, maybe it wasn't, wouldn't be obvious without actually doing experiments.
Yeah.
That will actually behave like a periodic system. That it's,
That's right.
that the disorder is weak enough, right?
Yeah.
And so we know from experiment that it does behave like a tunable artificial crystal.
Mhm.
But I think that, it becomes, the conditions on homogeneity and so on become exponentially more complicated if you have two moirés, right?
Yeah, you're talking about the realistic twist angle.
Yeah, yeah.
Yeah. It's
So I
it's
think
always
that,
there. Yeah.
I think that, if you have, two moirés, then that means that you probably, can think of it as one system that is being periodically modulated by the other. But actually seeing the periodicity of that modulation is, I think we're very far from having that degree of perfection. Let's say you might, for a system with two moirés, there are interesting mathematical questions about localizations of wave functions, things like that.
Mhm.
I don't think it's going to be, I don't think the systems are good enough yet to answer those questions experimentally. Although theorists will certainly look at them.
So even just a simple twisted bilayer with the same target twist angle.
Yeah.
Every device behaves slightly differently. Sometimes very
Yeah, the
different.
trilayers, you mean.
Tri-layers
Or
or
even
even
the
twisted bilayer.
Yeah,
Some are
Because-
more homogeneous, some are less.
Yeah.
We can always buy a rotator that has a 0.01 degree accuracy, but when they touch each other, they feel uncomfortable and they're relaxing, somewhat unpredictable way.
Yeah.
Yeah, trilayer tends to be, for sure, tends to be worse. I think I on the March meeting, I heard the talk from Ben Philman's group, who's also looking at this, but with this capacity, local compressibility measurement.
Right.
With a little bit of luck, maybe out of 10 or 20 samples, we can find one sample that is really homogeneous. Like even for this different. But homogeneous in a sense like a transport signature, while more or less a periodicity is well defined across a long distance, but perhaps not in a traditional sense where it's truly just a single crystal periodicity for sure.
Right.
Yeah.
Right. Yeah.
Very cool.
Anyway, yeah, nice chatting with
Yeah,
you.
nice chatting with you. Thank you very much.
Hi, you guys are together, I guess, are you? From, yeah, you want to talk about something specific? So you,
So we're seeing.
yeah,
And he's first.
okay. You are, who student?
I'm Boris student.
Okay,
I graduated last year. That's what John Cusp.
okay, excellent. Yeah. So what did you want to talk about?
So we're talking, so.
Yeah, you can sit there, yeah.
Very good.
Yeah.
So I have one quick question about the So you mentioned Wigner crystal, there's no magnetic field dependence. Critical density,
Yeah.
charge density. For example, in 9/11, you expect a straight line for B versus B, for example, for B versus, right? There's no-
yes, so
there's
density versus B,
density versus. B.
yeah.
So Y axis is B.
Yeah.
X axis is X. Yeah, it's straightforward.
Yeah,
So, and for turning, so there's a slope. There's slope from the largest,
Exactly,
far
exactly.
axis.
exactly.
So what about the temperature for charge density? What we do expect in single. What's the signatures?
So topologic, you mean like a churn crystal, like something like this.
Yeah, breaks the transmission signature.
Um. Yeah, so that would be, so, let me make sure I'm on the right page. So, you know, there is this interpretation of Longju's experiments.
Yes. Okay.
About the hollow crystals. They talk about that kind of state.
I don't have a clear distinction between hot crystals and, for example, what Andrew Young did, the topological transdensity. The translational symmetry is spontaneously broken and they get, for example, integer chain number, for example, at halfway.
Yeah, yeah. And that's in a magnetic field. Right,
That's
is that-
no weak, maybe small magnet.
Is that the one from 2020 or something?
Yeah, yes.
Then probably the magnetic fields are not all that weak.
Okay.
Yeah.
Uh-huh.
But, what I was trying to say is that whenever you see a quantum Hall effect,
Mhm.
it tells you that you have a gap
Mhm.
at a magnetic field dependent density.
Mhm.
So in a non-interacting system, you know, when you have a churn insulator, I guess, you know, that's kind of a surprising thing. But with interactions, it's even more surprising. So, if you have a magnetic field, you know, you can easily get. If you already have a field,
Mhm.
it's not surprising to have sensitivity to fields.
Yeah.
So I think that, yeah, anyway, I view phenomena seen at zero magnetic field differently. Yeah.
And using.
Yeah. Yeah.
I'm fresh air here.
Because I talked to.
Acting reschedule.
Yeah.
And I showed him, so I just played with, I'm not sure if I mentioned.
It wasn't be careful.
What was the T2 core model?
Yeah.
Functions.
Yeah.
Open now.
And then I mapped the
You don't change it because it's too confusing. It's like,
But
why?
hopefully
Okay.
the foot didn't change yet.
Well, I think it was going to be delivered.
It looks good actually.
Yeah.
Sign. Looks better than, I also signed up for
That is.
the workshop show.
So that if I use this formula, just P and
The
Q.
one that talking about the computation, combination of the computation.
Right.
So.
Oh, that,
you-
yeah.
Yeah.
Shoals.
Yeah, that was comparing.
Yeah.
The sandwich versus.
Okay.
But eventually I have the real space dependence.
Okay, okay, that's interesting.
And of course, I can also write down the singular section, turn on local
Okay.
number.
Mhm.
So that represents, I guess, edge state. So MR, so eventually, so the M.
But what you call C of R is periodic in space.
Yes.
Okay.
So MR eventually equals to the momentum space integration product just times density
Okay,
operator, density matrix rho R
okay,
for the NK state projected those.
okay.
Okay.
So that's like psi squared for the A. Is that what you mean by rho and A? This one?
Yeah.
Is that stand for wave function squared?
Wave function squared. Yes, so so it's R MK. Wave function squared, yes.
Okay,
Okay, and this MR also satisfy the maximum at a particular.
okay. Mhm.
So I just
Okay, I see. So it's a local version. Yeah,
yes, okay. And I just plot this in the MOT2
Okay.
model.
Mhm.
So so they can just row in row space for
Okay.
different bands. For the first band, so it looks
okay,
and just plot this MR. So because there's a rho and K function, so MR also represents these peak of densities
okay.
in various space.
Mhm.
So this is MR bulk part without displacement field. Okay.
Okay,
So here is localized on one top, for example, top layer, and this one is localized.
okay,
And if we add a displacement field, so because the displacement field can tolerate the chart
yeah,
to different layers, so it actually can have different even opposite sides. On the two layers or two sublayers.
okay.
This optimal compensation. And then I showed this to Shi, and he asked, and he said it is interesting because they are looking at the epsilons, because in epsilons Moiré stuff, Moiré lexia.
Yeah.
So it is optimal compensation. And also this
Okay.
Your pseudo real space. Pseudo magnetic
Yeah, yeah.
in real space coming from real pseudo space. Because this are in distribution is very different from this actually. So so now I just want to continue discuss. So I wonder because I don't know how this optimal competition can couple these things.
Yeah, it would be maybe interesting to try and calculate the magnetic field
Oh.
distribution outside of the sample. That's what's measured in the squid. So.
Coming from for example, I can imagine this part as this dimensional
Yeah.
equation.
Mhm. So,
And this one.
yeah. But there are formulas for the magnetic field created by current, right?
Yes,
in
yes,
EMF.
yes.
And the observer might be, these are 2D current loops. But the observer in practice is a squid, so they do these measurements with scanning squids.
Mhm.
And in principle, they can measure the distribution of magnetic. It should be possible, but right. to express.
So many of you.
But I wanted to mention purpose. PhD depends, but you are.
Yeah.
Who's always come to properly of currents and compressive regions. Ellie told me, he met you at a conference, he told you about.
That's certainly, that's certainly.
We're gonna take a.
Exactly.
Yeah. I remember this. It was.
For example,
Yeah, how would it affect the next?
or on the spin.
Yeah.
More or less equilibrium.
They can.
They don't couple.
Yeah.
I believe not.
Yeah, but we're doing the same for p-n junction. We always speak about drift current and diffusion current. You discuss the p-n junction. Yes, you have always these two parts, and there's some similarities. You have also the drift current in the incompressible medium and diffusion current in the compressible medium.
Maybe.
Whenever you have a magnetic moment to your current, whenever you have a very different density, you have a current.
Yeah.
This is also the case for Chern insulators. It is perfectly equivalent to London.
Yeah.
Since
The states that are
in the
occupied by
compressive
full-
regions,
fully these
full bands,
they're
we have all curve that drives this enormous velocity. We have
occupied
we have the
by, it's a bound state, states occupied by the light,
compressible regions.
everything in the band except for these guys.
And them.
Together we're gonna get that out of this.
Self-rotation.
Right?
The wave factor.
And that's the top problem, trying to make a bound state.
They have a magnetic moment.
Occupied the alternating state, make a quick conduction.
Generally counter-propagating, so they don't have to be counter-propagating in the. But generally, usually.
I would not be surprised if you looked at it, if there's some simple relationship between, like, in E&M books, I think there's formulas for B of R
Then there is a follow-up word from
sources and
Okay.
maybe it's the same formula that applies here.
4 or 5 years ago that I didn't fully digest, but he's talking about this counter-propagating compressible currents. So they may have some implications other than just, they have implications for the energetics of the system in the magnetic field because they create a magnetic moment. But they may also have implications of transport. Need to revive the communication.
How is the transition then to the classical behavior? If you go to higher temperature.
This is Landauerian magnetism, it oscillates, right? Landauerian magnetism has this. The oscillation, the positive negative oscillations, Landauerian magnetism is just these oscillations of dominating, you have excess edge, excess incompressible versus excess compressible. Yes, that's the.
Is just the.
And I, for some time, thought,
To me.
currency, quantum point is below currency.
Yeah.
Just like your paper with vice, right?
Yeah.
But now.
Edge.
That's.
These are very mature ways.
That is some percentage which is system dependent. For example, it only depends on the sharpness of the combined potential. Your work with the scanning SET goes on, or Kelvin probe goes on smooth.
It's always,
temperature. But if you consider graphing,
Graphing is much sharper.
Very sharp. And I think there is a recent paper that Phil Kim sent me about people who solve theoretically self-consistently electrostatics and quantum mechanics. And then they find some transition between two regimes, more edge-like carrier current and bottom carrier current. And I believe this is correct. And the reason why it's quantized, because both the contributors is the same. Well, you point out very nicely in your paper that it must be the inner motions. It's already the spirit to carry the gradient, right? Otherwise you divide two numbers in here. But given that, you can also have an addition chemical potential, so chemical
Yeah, this is.
that's the same exact. So I think the reason why this is somehow because there is probably this nice
Yeah, but only totally different in the
Okay, yeah, I have some charts. I think many people I'm as an outsider. No, that was
for you, absorb your dinner. So our next speaker is Aviram from MIT. Major.
So thank you. I hope you won't fall asleep and for that, please ask me questions as we go. So I know you're with me and we'll continue. Let me start by following up on all the previous speakers, and I'll tell you when I first met Boris, and it was 2 hours ago. You also remember that. But on, you know, I first met you single-sidedly on your seminal 1992 paper, Microscope and Glazman. We were working on F states in graphene, so I have to understand this compressible and incompressible picture, which is very useful. So today I will speak about a different subject, multi-moiré magic. Essentially, we have twisted tri-layer graphene. In this, I will show two recent works about this. So we have twisted tri-layer graphene, but this time we have two different twist angles, which results in two moiré patterns that are in general incommensurate with each other. So we get these moiré quasi-crystals, what we call. And in a different realization of two other twist angles, we get surprisingly some other kind of what we call polycrystals. So let me begin by introducing quasi-crystals. And these are these funny shaped crystals which were discovered some 4 decades ago. But although they were discovered some time ago, they're still very highly underexplored. First, because they are very scarce. Only 1 in 1,000 crystals is a quasi-crystal. And this just happens because, you know, the ground state of the structure is usually periodic. And you need a very specific stoichiometry, for example, here, to create this quasi-crystal. And this is also the reason why it's hard to engineer and tune. If you try to change a little bit the stoichiometry, you will end up with a periodic ground state. And similarly, if you try to dope the system, you may easily end up with a periodic structure. So these things make it more difficult to explore. And you know, theoretically, they're also difficult because since they're not periodic, Bloch's theory is out the window, and most of all we know about condensed matter physics goes out the window with it. However, there are some recent, reasons why we want to study quasi-crystals. For example, topological classification, novel quantum spin Hall effect, unconventional topological superconductivity. The latter also requires strong interactions. So our goal here would be to engineer strongly interacting and tunable quasi-crystals. Okay. But I haven't defined the quasi-crystal yet, so let me do it now. So a quasi-crystal is a solid with long-range order, but without periodicity. How is this possible? Usually we think of these two things as synonyms. So for example, this Penrose tiling never repeats, so it's not periodic. However, if you take the Fourier transform of this, we find sharp diffraction peaks indicating long-range order. Similarly, twisted bilayer graphene is a quasi-crystal, because for a general twist angle, it's not periodic. These are the atoms of layers 1 in red and 2 in blue. So they're not periodic. However, obviously the Fourier transform is sharp. So it has long range order. Namely, if I tell you the positions of the atoms near the origin, you can infer the positions of the atoms arbitrarily far away. So it has long range order. Now this crystal, you can see it takes 4 lattice vectors to construct it. So we call it a rank 4 quasi-crystal. The rank is the number of lattice vectors required to form a crystal. And usually in the conventional periodic crystals, the rank is equal to the dimension. So the 2-dimensional crystal requires 2 lattice vectors to span. And in fact, there is this criteria. If the rank is larger than the dimension, it tells us we're dealing with a quasi-crystal. So I told you bilayer graphene is a quasi-crystal. So indeed, the atomic structure here is a quasi-crystal. And let's look at the Dirac points of layers 1 and 2 and let them hybridize here. If the angle is large, this hybridization happens on the electron scale. And the energies we can access with the chemical potential are low. So essentially the electrons that live, the electrons either live on layer 1 or on layer 2 and they're completely unaware of the other layers. So each one of them sees the periodic potential. So if I try to, if I still want to use graphene or van der Waals materials as my platform to engineer quasi-crystals, what do? I want to reduce the energy of this hybridization. So let me rotate to a lower twist angle like this and then hybridize. So now the hybridization happens at lower energies and the electrons know about 2 layers. Okay, so maybe now I get a quasi-crystal. But sadly, although the atomic structure is a rank 4 quasi-crystal, what Allan MacDonald taught us a few years back is that the low energy electronic states are described by this periodic moiré. So they don't care about the exact jitter of the atomic lattice between AA here and AA there. They just see this average, periodic moiré here. Purple indicates AA points and white indicates AD or BA. So what we'll do in this work is instead of using the atomic lattice as the building block for the quasi-crystal, we'll use the moiré as the building block. And the trick will just be to add another bilayer with a different twist angle. Again, the electrons see this periodic moiré potential, rank 2, right? But this time it has a different lattice constant. And if I now combine these 2 bilayers, and specifically I have them share the middle layer between them, now I have a tri-layer forming 2 moiré patterns, moiré 1, 2 between the bottom 2 layers, and moiré 2, 3 between the top 2 layers. And when I combine them here, what I find is this structure. So now the electrons cannot ignore the moiré 1, 2, they cannot ignore moiré 2, 3, so they see this low energy rank 4 moiré quasi-crystal. We call it moiré quasi-crystal for this reason. And of course, atomically, it's a rank 6 quasi-crystal, but the electrons don't care about that. The orange electrons, they see this rank 4 moiré quasi-crystal. So we have now a way by, just tuning the 2 twist angles, we can tune the 2 moiré patterns, so we can engineer these quasi-crystals. Importantly, the density scale is tunable with electrostatic gates. That's one of the major advantages of moiré. And lessons we learned from magic angle graphing is that if we choose the angles wisely, we can get high density states and strong interactions. So in this space of the 2 twist angles, theta 1, 2, and theta 2, 3, we have these 2 quadrants. One is alternating, where the two twist angles are in one direction, then I twist in one direction, and then I twist in another direction. We have this helical quadrant where I twist in the same direction 2 times. And I can put, systems we know on this map. This line is twisted monobilayer graphene, so the top 2 layers are aligned, and I only have the bottom layer twisted. Or you can think of it, magic angle twisted bilayer graphene. You can maybe put it here if you think of the top 2 layers just as one layer. The magic angle twisted trilayer graphene will be here at 1.5 minus 1.5 degrees, so in the alternating quadrant. Now I can ask, okay, so in this space, where do I expect moiré quasi-crystals to exist? The answer is quite simple. There are these 2 lines. Only in these 2 lines do I have a single moiré pattern. Okay, so either the top 2 layers are aligned, or layers 1 and 2 are aligned, and I get a single moiré pattern, so I get a periodic moiré. What I claim is that in all the rest of the space, I have 2 moiré patterns, and in general, they're implements with each other, forming a moiré quasi-crystal. So all this space should host different, realizations of moiré quasi-crystals. So in what I'll show first, the first part of the talk will show results, experimental results on a system here at 1.4 and minus 1.9 degrees, which is in fact what I'm already plotting here. This is what it looks like. Okay. This project is done together with Sergio, Malika, and Danny in Ray and Pablo's groups, and with theory support from Rita from Liang's group at the time, now in Stanford. So we have our twisted trilayer graphene is dually gated, encapsulated in boron nitride. This is the RXX 4-point resistance measurement in logarithmic scale versus carrier density and displacement field. You can see the charge neutrality point Dirac peak here, and you can see these 2 high resistance peaks that resemble what we know from magic angle graphene, bilayer and trilayer graphene as full filling of the moiré unit cell. Only here they are asymmetric in D field. And the asymmetry in D field is Z goes to minus Z. The asymmetry is simply because we have 2 different twist angles. Okay. Now, indeed these high resistance points correspond to fulfilling of one of the moiré patterns, and I can use them to extract the twist angle. So if this is my 2 moiré patterns, focus on the purple moiré pattern, is the longer wavelength one. If I put 4 electrons per moiré there, I may expect a single particle gap, but I have still the 3rd layer shunting the current, which will reduce the diminish significantly the resistance peak. However, if I apply strong displacement field, I can deplete all the carriers from the monolayer here and have all the 4 electrons per unit cell only on this bilayer here and retrieve the resistance peak. And indeed, this is what happens, and we can extract this angle of 1.4 degrees from this resistance peak. And similarly, this other resistance peak corresponds to filling 4 electrons per yellow moiré unit cell, so the top one, where we deplete the carriers from the bottom layer so that it doesn't shunt the current. And from this, we can extract 1.9 degrees. And we know the sign is negative here because we were stacking it in an alternating manner.
Why don't we care about the twisting angle between 1st and 3rd?
We do. In fact, this is an oversimplified picture that works consistently with the calculations. And I don't know why it works, but we were lucky enough that it does. It's really not as simple as that. So it's not like that the carriers live there and then this system becomes a more periodic system and they ignore the 3rd layer. Yes.
Yeah. One more question. Why is the 2nd moiré not symmetric? Why is like
Here?
this? Yeah, it's a little bit.
It's a good question. Possibly electrostatics because of asymmetry between the BNs. Let me think about it. No, sorry. So, okay, the fact that this looks like this is an expression of electron hole symmetry, and it could be that it's just mildly electron hole asymmetric, and that's why these guys don't appear symmetric. Okay, an important feature of this system is that we can tune between quasi-periodic version and periodic-like version. Let me describe this, what I mean. So what I'm plotting here is not the band structure because this is not the block system. We don't have a band structure. However, we can calculate what we call the spectral function. And the spectral function is, you can think of it just as the result of the surface experiment. So how much weight of the states do we have in momentum and energy? And this is calculated for a single particle picture. And we're taking a line cut through the 3 Dirac points as illustrated here in the inset. And the color represents the relative weight of the wave function on the 3 layers. Okay? So what you need to think about is you have an energy eigenstate, but it's no longer a momentum energy eigenstate because the system is not periodic. Rather, each energy eigenstate is comprised of superposition of different momenta. This is similar to a disordered system that couples different momenta together. So what we see here are 3 Dirac cones, okay, that are layer polarized. So there is a Dirac cone center that's K2, one at K1, and one at K3, and they have the corresponding layer character in their color. We see this flat band, quote unquote, of states and this fast band. And this should remind you very much magic and acoustic bilayer graphing. And indeed, we're close in the parameter space to magic and acoustic bilayer graphing. And importantly, you can see some of these lines are thick, and some of these lines are thin. They're actually points, many points that are small points. And what this tells you, if you see a large thick line or a large dot, this means it's a plane wave-like state. So most of the state, almost all of the weight, of the state is at a specific momentum. Whereas here you have broken up the state into different momenta. So this is what we call the periodic-like regime, and this would be the quasi-periodic regime. And we actually see this very clearly in transport. So if now I apply one test on magnetic field, and I take the same MD map and then look at RXX again, you can see that here at low energies, we have nearly visible Landau levels coming from the flat band, whereas higher up in energy, these are smeared due to the quasi-periodic scattering of the system. If I calculate the density of states and find these 2 sharp peaks with quite a high density of states, and importantly, they align with the quasi-periodic regime. So I have the high density of states of this system is in this region of strong quasi-periodicity. If I now look at the whole density map, I find this isospin symmetry breaking. You can look at on the electron side, you see a von Hoff singularity, so you expect from a single particle picture. But here, the von Hoff singularity is absent. And if I take a line cut, I can see the whole density goes up, and then at some point it's diminished due to a reset-like behavior, like this Dirac reset we know from other Moiré systems. So we believe the same thing happens here, so that we have symmetry, isospin symmetry breaking.
So this is a weaker effect than typically. Do you have a reason for that?
It could be that there are a few things you can just explain. Oh, maybe you're a little bit off magic. We don't have 10 samples, we have 1.
Okay.
So it could be that we're a little bit off the flat band conditions, and that's why everything is a little bit weaker. You'll see soon other things that are weaker as well. This RXX map, Landau fan also corroborates this picture. You see a 4-fold fan here, and then a new fan is born here. And if you trace this down, you see that it happens at carrier density that roughly correspond to a -2 filling of the small angle bottom right. Now, when we cool down and measure RXX without magnetic field, we find these 2 blobs of superconductivity. They are only on the whole side, and this is Charlie neutrality point. They're only on the whole side. We don't see superconductivity on the electron side, and they're kind of on both sides of this isospin symmetry breaking phase transition. So this trace is roughly equal -2 of the bottom line. Yes.
You understand why there's a large electron hole asymmetry in the Hall response?
No. I mean, it looks like this is consistent. These 2 maps are consistent. That you have. It looks like higher density of states on the whole side that drives more interactive physics here and superconductivity as well. So these 2 results at least are consistent, but our calculation does not see this. If I park my N and D here and I take IVs, I find this nonlinear curves characteristic of superconducting state. with a critical current of about 50 nanoamps. And the PKT transition temperature is peaks at 350 milliK. And the coherence length dips at the optimal point to 70 nanometers. So this is larger than the best magic angle graphene systems, which would be of order interparticle distance would be of order 10 nanometers. So still quite small. And we can play the game to estimate, to try to see if we're in this strong coupling regime. So we can compare psi over t, the coherence length over the interparticle distance, whether our Cooper pairs are strongly overlapping, like in BCS theory, or are strongly far away from each other, or in the ultra strong coupling crossover psi over d is order 1, which is the case for magic angle binary graphene. And we find that psi over d is of order 10. So, far from BCS, but not all the way to the ultra strong crossover, ultra strong coupling crossover, sorry. But we take it as evident to some strong couplings in the clinic.
Size from HC2.
Sorry?
You find psi from HC2 temperature dependence.
Yes.
Extrapolating to it.
Yes.
And is it a good thing to do?
Maybe not. Maybe not. You can explain to me why.
He used on BCS, right? So assuming that there's a.
Yeah, we do what we can, I guess.
But in terms of, if you look at the resistivity curve in magnetic field, is there some tail of fine resistivity at low temperature at low temperatures?
I'll comment on that in the end. Not in this system.
Okay.
So if I now take the superconducting map and superimpose the superconducting pockets on the map I showed you previously with the Lambda levels, I can say that the superconducting state happens where the system is strongly quasi-periodic. Okay, so I'm not claiming that quasi-periodicity drives superconductivity, but that they live together. And if I now put the superconducting pockets where the density happens on the calculated density of states, and I look at this energy and I plot the spectral function. So now you're seeing a constant energy cut of versus kx, ky of the spectral function. It looks like this, the calculated spectral function. These are the 3 Dirac points, and this is inverse moiré region roughly, and you can, as I said, each of the eigenstates in the quasi-periodic regime, each of the energy eigenstates is superposition of different momenta. So let's say it's this kind of superposition.
Why is it 3 key point is lines up? Because I thought
they're on a circle, center of the graphene, monolayer graphene gamma point is here, and you have these hexagons.
so it should not lines up with there.
Sorry?
There's some curvature should be there between.
Yeah. There is a very small curvature. I mean,
This angle you look like the 1 line. Okay.
It's a big circle. This is 1.4 minus 1.8. So let's say, just for illustration purposes, I have a superposition of these phase states that I plotted here by hand. Now, if I think of a nodal intra-valley pairing, so let's say a D wave kind of pairing within the valley, then I expect this quasi-periodic mixing to suppress superconductivity. However, if I would have no nodes within the valley, because of Anderson's theorem, I expect superconductivity to survive and to be independent of the quasi-periodic mixing. And this is, some statement. I can't say it's I can't say anything very strong experimentally yet, but at least in some indication, we still have superconductivity in spite of the intra-valley mixing. And it's an interesting kind of mixing, as opposed to maybe disorder that can mix different valleys. Here, the mixing is only within the valley because it's this moiré quantity. Another question that arises from inspecting the system is the role of C-to-C symmetry. We know that so far, if we exclude Vernel and ABC graphene, in Moiré systems, superconductivity happens in C2C symmetric systems. And in this system, interestingly, you have Moiré 1-2 and Moiré 2-3. They slowly, shift in space with some very large super Moiré lengths. So you will have regions in space that are C6 symmetric, and other regions in space, say 200 nanometers or 500 nanometers away, that should be C3 symmetric. So maybe we have some modulation of the superconductivity in space, and this is something that would be interesting to look at with local probes. This is the super Moiré structure. The red and blue are C2C broken regions, and the white is C2C symmetric. The scale is 200 nanometers. So this is without disorder. Of course, this will be distorted, but generally, it will have some kind of modulation of C2C symmetry on the super Moiré. Okay, so this concludes this part. I was showing you 1.4 minus 1.9 Moiré quasi-crystal. And in fact, if you think about it, we tuned from magic and implicit twilight into this system, and we saw strong correlations. And if you look at this paper here, Yang, they show, this is Tritup's group, they show that there is in fact a magic line, so a continuum of magic systems. If you detune one angle and you compensate with the other, you can remain on this flat band conditions. Okay, so for the second part of my talk, when do I need to?
You have 15 minutes.
15 minutes, right? So in the second part of my talk, I will describe this other system we call helical twilight. So now we were asking the question, okay, in this space, where do we go now? And we were thinking, what about this high symmetry line here? This high symmetry line here represents this system. We twist with the same angle in the same direction twice, theta, theta. What happens is that you get Moiré 1-2 and Moiré 2-3 with the same lattice constant, but they're twisted with respect to each other with the angle theta. So if I zoom out, now these dots represent the Moiré AA of layers 1-2 and AA of layers 2-3. So these are not atoms, these are Moiré mid-cells. And I find this very large length scale super Moiré. Lambda super Moiré is lambda Moiré over theta, therefore it's the atomic lattice constant in theta squared of order 200 nanometers. And because the super Moiré is much larger than the Moiré, I can think of a local vent structure for a given shift between the two Moiré patterns. So I can have a Bistritzer-MacDonald model, generalized model for 3 layers that is space dependent and parameterized by the shift between Moiré 1-2 and Moiré 2-3. So this is the model I have. I parameterize by this shift P. And for example, if I zoom in here, I find the 2 Moiré patterns are on top of each other. So this is the AAA region, but there are other regions that the Moiré patterns are shifted in one way or shifted in another way. If I calculate, or Tritup calculates, the density of states versus twist angle and average over all the different shifts, this is what we get. So we know we should aim for a magic angle of 1.8 degrees when we have the samples. So this is what we did. We went here. This work was led by Chow, together with Sergio and Aaron from Papa's group. And again, Tritup on theory together with Gibbs and Patrick. We made these dual gated devices, and this is RxX again versus their density and displacement field. You see now a very strong electron hole symmetry, and you see correlated states at integers 1, 2, 3, and at 3 halves, 7 halves, I'm sorry, 3.5. The hole density map shows a Van Hoff singularity here that corresponds very well to the calculated map that we have. And importantly, here we see this Dirac reset similar to what we saw in the Moiré quasi-crystal on the hole side. When we go to neutral 3, we sweep magnetic field and we find anomalous Hall effect. Okay, it's not quantized; it's like plus minus 2 kilo, but we still believe it has to do with Chern physics. Similarly, we see at mu equal 1, we see also anomalous Hall effect, a weaker one, but it's definitely there. And if we change the temperature, we see a Curie temperature of about 10 Kelvin and mu equal 3 and about 5 Kelvin for mu equal 1. And this Curie temperature is in fact the highest reported in the graphene system. It's exceeded by the 14 Kelvin of the Moiré TMDs. You can see that the resistance, as we tune displacement field, it goes down and then it goes up again. This looks like some gap closing and reopening, some correlated gap closing and reopening. And we believe that this is topological phase transitions that are happening here. The reason we believe that is because here we find anomalous Hall effect, but here we do not find it. So the bands are topological here and become non-topological about the phase transition. This theory paper does the calculation, and we can see we have a gap closing and reopening, and the bands start topological, become non-topological, higher T phase. But there is a big puzzle that you may have not noticed because I'm running quite fast. But if you remember, I told you we're looking at quasi-crystals. All this blue space should have been quasi-crystals, not periodic, right? But I'm telling you about churn physics. Definitely you need a band for churn physics, right? So how is churn physics possible in a quasi-crystal? And another question is, how can a C2Z symmetric crystal support very curvature? So this is 3 layers of graphene that are twisted in the same direction, whatever. But if I rotate this system 180 degrees, that comes back to itself. And we want to break C2T to have very curvature at all, right? And all of these previous systems that show anomalous Hall effect or quantum anomalous Hall effect break C2. So it's either magic anchor graphene aligned to boronitride, or it's twisted monopi, where the pi layer is AB, it breaks C2. So here we were like scratching our heads for some time, what's going on? Why at all do we see churn physics? Because of these two reasons, not periodic and C2Z symmetry. So the answer is related to this work from Philip's group, where they found that if at small twist angle, specifically below 1 degree, the lattice relaxation is very important, and you create these domains of AB or BA, separated by thin domain walls. But we have 1.8 degrees, so we don't expect lattice relaxation to do much. Okay? And indeed, lattice relaxation on the Moiré scale doesn't do much, but on the super Moiré scale, it does a lot. So what happens is that the system prefers specific arrangements, namely this delta shift or this other minus delta shift, where the 2 Moiré, the AA12 and AA23 are kind of maximally shifted with respect to each other. And it doesn't like the AAA stacking for the helical arrangement. In fact, if you remember Abhai's paper about magic angle twisted trilayer, where it's alternating twist, they find that the system prefers A twist A. So it seems that the helical arrangements prefer this maximally shifted arrangement. In any case, we have these large regions. The color here, by the way, represents how periodic is the system or how aperiodic it is. So you find these large triangles of order 200 nanometers, and the system is periodic Moiré system. So it can support locally, it can support bands, and it breaks C2. So it can support a very curvature. Right. Now, the last ingredient, we need strong interactions to break counter versus symmetry, and therefore we believe we see an anomalous Hall effect. Now, the system is globally still C2Z symmetric. If you rotate about this point, the system comes back to itself. There are a few points you can rotate about, and the system comes back to itself, but locally it breaks C2. So we call this system a Moiré polycrystal, and just because we have this, stitched together different crystals, 5 minutes. In momentum space, the relaxation, you start with the K points on a circle, and then relaxation pushes them to be on a line, forming a periodic system. And now we can use this delta shift to calculate the band structure within a domain. We find this density of states. Again, the magic number is still about 1.8 degrees. And the band structure looks like this. We have, and we feel this is an important slide, maybe theoretical, but important, that we find these two Chern bands within a domain of Chern number -2 and +1 for a given value. The other value will have the opposite numbers.
This is the super-moiré Brillouin zone or the
This is the Moiré Brillouin zone.
moiré Brillouin?
We're now zooming in on one triangular domain like this, what they call like one of the Moiré domains.
Okay.
And we assume the system is infinitely like that. So this is the Moiré. We find these two bands. In fact, this is an important comment. Sometimes people talk about super Moiré as a periodicity. I don't believe in this concept because the tiniest, distortion will create crazy super Moiré. So I don't think we have a periodic super Moiré, but I do think within the super Moiré we have these patches of nearly periodic Moiré. And then importantly, we have a huge remote gap of over 100 million electron volt. And there are these hierarchy of energy scales forming a strongly interacting limit. Right? These bands remain flat despite interactions. So in contrast to magic angular graphene, which requires a large dispersion when you dope it with electrons to the Coulomb. Here, because we have AA12 and AA23, the charge distribution is more homogeneous. And when you dope electrons into the system, the bands remain flat, we believe. There is near ideal quantum geometry that I don't have time to show, but we believe it's favorable for FCIs, fractal Turing series. Lastly, a feature of this system is that it has this topologically protected edge modes. If you focus on value k going from one domain, we call H, and this we call H bar, H to G. So if you go from one domain to the other domain, for a given value, you find that the total Chern number of the flat bands changes from -1 to +1. Therefore, you must close the remote gap on the boundary between these domains. This is quite similar to ABPA in marginally twisted 5-year graphene. So we believe there are these topologically protected edge states. Now coming to the end of my talk, so I showed you this line here, and I didn't mention, but we have this other work in progress now on this point here, 1.2 minus 2.4. And this has to do with your question, does the resistance saturate? This is not yet, this is work in progress, but we find superconductivity there as well. And it smells like some kind of anomalous metal. In that the resistance doesn't go quite to zero, in contrast to what's happening here. And we think, and we have some idea why that is. Essentially, it has to do with this modulation of the density of states on the super-Moiré scale. And each one of these systems has to be treated separately, and it's unique, and we can chat about it later. I showed you this point here, helical triangular graphene at this magic angle, and in fact, you may have guessed that this is also part of another magic line. So we have some other stuff to explore. In fact, we're now looking at this system as well, which also shows strong correlations. I will skip this, but relaxation is crucial. So I refer you to this paper if you want to understand a little bit more about these systems. We have these Moiré polycrystals where the relaxation makes large regions of the same kind of shift versus other systems that we believe to be Moiré quasi-crystals. So I would like to thank all the wonderful people I worked with on this project. And to summarize, I've shown you these Moiré quasi-crystals, all this blue space here, that are strongly interacting, highly tunable and engineerable. And maybe can teach us some lessons on Moiré productivity. I've shown you helical triangular graphene, which is flat isolated with rigid bands and with topologically protected edge modes. And I wish to claim that multi-moiré is a large phase space for strong interactions Each each of these systems is unique and must be considered separately, and with relaxation and all that. And we find signatures of different physics happening in these different systems. And this is just, tri-layer graphene. You can think of other material platforms to do this. So, with that, thank you.
All right, we have was chance to ask magician to reveal. Peter.
So I wonder whether one can treat kind of very similar treatment onto the alternating twist angle. In other words, rather than looking at this quasi-crystal kind of the frame, can I just look at this super moiré type of things, right? And just kind of go for the long wavelengths type of the MacDonald distributions.
Okay, excellent question. So I think what Philip is asking me, and correctly if I'm wrong, the quasi crystal I was talking about here, maybe you can also think of it just as a super moiré. So the answer is this. To me, this quasi crystal, which has an approximate periodicity of a 3x3 and 4x4 moiré unit cells. Maybe I have it down here. Easier to sorry. Yeah, this. Okay. So this is you can maybe see that it looks like almost periodic, on this periodicity. So there is also some periodic like maybe structure. First of all, to the best of our understanding, this thing doesn't remain the same exactly. It's shifting in space slowly, and it doesn't relax into precisely periodic domains like this.
I thought kind of some of the RBI's experiments was exactly done onto this alternate twist angle. And they report, didn't they report kind of some of the moiré type of the structures?
Are you referring to alternating twist theta minus theta?
Yeah.
Or magic angle twisted triangle graphene, right?
Yeah.
Sorry, so I didn't understand your question before, but yes, in magic angle twisted triangle graphene, if you have 1.5 and 1.50 minus 1.55, is that the case?
Right, so something like this. I mean, you cannot always kind of match the angle exactly, right? So
the alternating, this is this.
Let's go to the phase diagram and yeah.
So this is magic angle twisted triangle graphene with slightly different twist angles, unrelaxed. And this is relaxed. In the relaxed structure, you see that it prefers this AAA or A twist A regions and it enlarges them. It expands them. And this is exactly what Allan measured in his experiment, right? And in contrast, in the moiré quasi-crystal we measured, what happens is this is the relaxed structure. It looks almost like the unrelaxed structure. So there is some deformation, but it doesn't lock into a specific arrangement. So on the super moiré scale, it's going to change a little bit. But to me, even just looking at a single unit cell here or here doesn't matter. A single unit cell, it has the pseudo periodicity has 25 moiré units, AA moiré unit cells, 9 from the bottom two layers and 16 from the top, 9 purple and 16 yellow. On the density scale of the moiré, on the 10 to the 12 scale, already is to be a quasi-crystal. You see what I mean?
Maybe we can discuss it later separately. Yeah.
Right. Questions?
Yeah, okay.
Very short one.
Okay, I have is my understanding correct that overall the helical twisted trilayers overall topologically trivial, and because you see anomalous Hall effect is because you like the size of the domain is comparable to the distance.
Exactly.
Okay.
Yeah. It doesn't compensate fully, yes.
All right, I'm afraid we need to move on. All right. Our last speaker is Brian Skinner from Ohio. And we couldn't get a debate about Wigner crystal. There's something about it. So here's the time. I'll show 10 minutes.
Yeah, and just so you appreciate this, I made a whole new talk last night so that I could talk to you about Wigner crystals. Despite the fact that I'm very sleep deprived from having a new baby, but we couldn't have a conversation about Wigner crystals. Okay, let's have a better. Okay, first of all, I feel like I should apologize. It's kind of bad behavior in general for an organizer to also be a speaker. But I think it was decided among the planning committee that my role as a Shklovsky student takes precedence over my role as an organizer. So I'm going to try to talk about Wigner crystals. I'm going to introduce two new ingredients to them. One is a different kind of dispersion relation than the usual p-squared, and the other one is very curvature. See how these things are together. This is really work done by my student Sandeep Choi, who's in the audience, and they'll be starting as a postdoc at Florida State in the fall, with some input from Leonid they'll be taught as well. We got in there. Here. So Wigner crystallization is definitely a disease that I caught from Boris, the obsession with Wigner crystallization. Actually, last night I looked up how many papers did we write together while I was a student that invoked the concept of Wigner crystal, and the answer is 10. So in my 6 years as a student, we wrote 10 papers together that at least used the concept of Wigner crystals. And I'm going to hopefully show you today that that obsession has been paying some dividends lately. Okay, I probably don't really need to introduce the concept of Wigner crystal. There are some students in the audience, perhaps. The history is really, it came out of the very early days of physics metals, 1954. We're what, 6 years past Planck's theorem. And they were thinking about what's the interaction corrections to the energy of electrons and metals. And what had been done so far was sort of Hartree-Fock theory and understanding the exchange interaction. And then Wigner wrote this paper pointing out that if the interactions are strong enough, then the electrons will repel each other so strongly that you'll get a modification of the wave function. This later determined wave function will no longer be the right wave function to describe a system of electrons and metals. And in fact, he points out that if the electrons had no kinetic energy at all, then it would be easy to write down their state. They would just crystallize into some kind of crystalline arrangement where they maximize their separation from each other while maintaining an overall density. And what's the region that corresponds to no kinetic energy? That's basically the region where the interaction energy is much, much bigger than kinetic energy. So I think the interaction energy E squared over R, the kinetic energy H squared over M. And that basically corresponds to this being much larger than that one, which is the limit of very low density. So if electrons are very, very sparse, then maybe counterintuitively, their interaction becomes much, much bigger than their kinetic energy, and they can become classical. So it's become sort of fashionable lately to refer to a Wigner crystal as a quantum crystal, but Wigner understood that a Wigner crystal is basically a classical object. It's the limit where quantum mechanics don't, enters only as a correction to the classical. Okay, so how do you think about this correction? This is something that I learned very clearly from Boris. So you think that the electrons in 2 dimensions crystallize themselves in some triangular lattice where they're avoiding each other to the best of their ability. And again, that corresponds to the limit of large ratio between Coulomb energy and Fermi energy. You can write that as this interaction parameter Rs, which is basically the distance between electrons in units of the effective Fourier radius. The Fourier radius has material parameters, dielectric constant mass. But you can think Rs is basically the distance between electrons when it's very, very big, and the interaction is very strong, relatively strong, and you enter this crystalline region. This is a classical picture. So a Wigner crystal is basically a classical object, classical triangular lattice. It's what you would have said electrons would do if no one had ever touched quantum mechanics. So how do you incorporate the effects of quantum mechanics to the lowest order in your conceptual thinking? Well, you say that, well, actually, if I remember that quantum mechanics exists, then I should say that each electron is like a little harmonic oscillator that sits in a confining potential between lights. So these neighbors create a sort of potential well that this one electron is sitting in, and then you say, okay, well, if the electrons are far enough apart, then that potential well looks locally like a parabolic minimum, and the electron just forms a ground state of a harmonic oscillator, and then that ground state has some size, and the Wigner crystal limit is exactly the limit where this size is much, much smaller than the Wigner lattice constant. Just to be clear, this, what I call the Wigner lattice, has no relation to the underlying crystal lattice of the material. It's a spontaneous. Okay, so this is a heuristic picture that Lawrence taught me very well. If you really want to calculate the energy, the ground state energy of a Wigner crystal, how do you do a proper calculation? Well, the proper calculation is you write down, some coupled equations of motions for many electrons swinging in triangular lattice interacting with the Coulomb interaction, and you realize that they have phonon modes, they have collected mode, longitudinal and transverse phonon mode. You calculate the full dispersion relation by diagonalizing that equation of motion for all the interacting electrons. And then you assign 1/2 h omega of 0-point energy to each phonon mode. Do that calculation, you don't actually do it, you look it up in Mayhem or something. You get an expression that looks like this. So this term right here, which looks like E squared over R, the lattice constant, this is that classical energy, the energy of just classical point charges sitting on a neutral plasma background. It's negative because the electrons are more attracted to the background than they are from each other. And this is the first quantum mechanical correction that comes from that 0-point motion of electrons sitting in that confined position. This is how you do a proper calculation. This, you can read about it in Mossel and Martin, for example, 7. One of the things I learned very well from Boris is that you shouldn't do a proper calculation if you can do an improper calculation. Proper calculations are often hard and time consuming and they obscure the physics. Improper calculations can be done very quickly, give you lots of physical insight and get the answer right in factor 2. So let's do the improper calculation. Which is basically the way I told you. Just treat each electron as sitting in a parabolic well. You can pin the locations of all the other electrons in place, calculate just by doing some sum. Well, what's the shape of this confined potential to lowest order? And then you just say the energy is the classical Nettling energy plus h omega. And if you do that calculation, you'll get this expression right here. You notice it looks basically identical to the proper one that I told you about. The only difference is that this number is 1.77 instead over here it was 1.63. So you're 9% off, and then you're very excited that you didn't do the real. It also gives you some insight about what's happening and when is this going to melt. So from this calculation, you think it's basically a single electron quantum. You think about the electrons that kind of harmonic oscillate their wave packet, the really nice wave packet has a characteristic size. The size of that wave packet works out to be this, and you say, oh well, the wave packet is much smaller than the Wigner lattice constant. Whenever the distance between electrons is much bigger than 4 radius. So that already gives you some idea of when the Wigner crystal is going to melt. So in particular, we have a Lindemann criterion that says if you push it to the point where this size becomes some critical fraction of the lattice constant. Actually, it's kind of a mysterious coincidence that the Lindemann criterion works remarkably well in all 2D systems that I've seen when you set this ratio somewhere between 0.21 and 0.5. So let's be democratic. Anyway, what I want to say is you can do this very simple calculation. It's basically a single particle calculation. You get an estimate of where does the Wigner crystal exist, what is ground state energy, and when does it melt. And that's the calculation we're going to do. Okay, so literally 90 years after Wigner's prediction, Wigner crystals are in the news again in a bunch of contexts. We're starting to see them. So there were some nice optical experiments in the TMDs, basically seeing evidence of the Wigner lattice in terms of plume cloud scatter. You can see it by locking two parallel Wigner crystals also in TMDs. There have been some nice transport experiments quite recently, sort of heroic transport experiments. And this is all at zero magnetic field. That C emerges a very strong pinning in the IV curve when you go to RS above about 30, which is where the best theories predict the crystal should exist. So this curve here, sorry, this is IV that you're seeing. And above a certain critical field, the current suddenly appears, and this is associated with a sliding or deep pinning of the Wigner crystal, allowing current to be carried. And this pinning turns on very abruptly above the crest. Maybe most dramatically, just this happened in the last half year or so, we have some experiments directly visualizing the Wigner crystal by STM. So this is in graphene high magnetic field. This is a TMD at V equals 0. It's really just STM directly visualizing. All this is to say, 90 years later, Wigner crystals are hot again, and the obsession with Boris Gate is paying off. So let's. Okay, maybe I should. It's liquid helium temperature, but hot metaphor. Okay, so the new ingredients that I want to add here are what happens if the dispersion relation is not parabolic, meaning the underlying dispersion is not p squared over 2m. And what happens if you have barrier curvature? How do those things modify the nature of the system? And the motivation was really came from reading this paper coming out of the Santa Barbara group, where they took AB bilayer, so sorry, no moiré stuff, man, just a simple man, just AB bilayer, no twisting. What used to be called just bilayer. And you can measure, say, the resistance as a function of the electron concentration, A voltage, and the displacement field, meaning a difference in potential energy between the top and the bottom of the layer. And you see all this like beautiful phase transitions between different symmetry broken metallic phases. These are all conducting phases, and there's a whole cascade of phase transitions between one symmetry or another being broken, spin, valley, etc. But the part that inspired us was this part where there's nothing happening, this white area right here, where there are sort of low density insulating phases. So all this white that they didn't even bother to color has high resistance, it's insulating, has an insulating electron dependence. And then you ask, well, what's happening here? And the obvious answer is that's just a band insulator. But literally speaking, if it were a band insulator should exist only n equals 0. You put any finite number of electrons in the conduction band, it should be conductor. You say, well, maybe it's an Anderson insulator, but maybe it's not. Maybe this is some other more interesting insulating state, like a Wigner crystal, where the electrons form this crystalline arrangement, and they can't conduct as any finite disorder. So now the basic question is it possible that somewhere in this white region you have a Wigner crystal? And if so, where would it exist in the phase diagram? And is there something unusual about it? Okay, so the first point I want to make is that you can't have a Wigner crystal in bilayer graphene without a displacement. And when you look at it at first, it seems like, okay, a bilayer graphene at 0 displacement field has sort of two parabolic bands attached to the point. That's not literally true, but I'll bring back to the in a second. So you say, so there's a finite wall radius, so there should be a finite RS, finite critical concentration associated with Wigner crystallization. That's what you expect for a no parabolic band. Turns out to not be true in this case, because the gaplessness of the band structure implies that you can get a very large role of virtual interband excitations. You promote a hole from the valence band into the conduction band in some virtual way, and you get a huge role of interband dielectric screening.
And it's stable if there's no excitonic transition to.
Let me ignore, yes, so there can also be an excitonic instability. That's a very, very subtle question. But actually, let me come back to it in 30 seconds.
Okay.
So the point I'm saying here is that because of this strong interband dielectric response, the Coulomb interaction is not E squared of R. And instead, it becomes something that's only E squared of R at short distances and becomes 1 over R cubed at long distances. And what corresponds to short and long is exactly the coordinates. So the Coulomb interaction, because of this dielectric screening, becomes essentially 1 over R cubed, distances bigger than the Bohr radius. And if the Coulomb interaction is short range, it can't support Wigner crystals. So no Wigner crystals until you open it. Now the question was about whether there should have been an excitonic instability in the first place. My understanding is this is a quite subtle question, precisely for this reason. You know, excitonic instability says I promote an electron in a hole and then I bind them together and lower the energy and end up with a gap. But if the Coulomb interaction is truncated, then I can't form a bounce link between the electron and the hole in the first place. So as far as I know, the most careful calculations suggest that there could be a gap here, but it's very, very small. It depends inversely on the whole band. But I actually don't know the status of that. So let me, because from now on, what I'm going to do is I'm going to gap out the conduction field.
But would it mean that then at large distances you restore 1 over R or not? If there is a field. Maybe it's just not important because
You have to open a gap to restore 1 over R.
Yeah,
If you open a gap, then at large enough distances, then you will restore 1 over R.
okay. Just an experimental point. When they plot density, they're really plotting gate voltage. Often
Yes.
they have not corrected for density of states variations.
Yes.
So if the band gap is getting wider as you go up in displacement field, which it should,
Yeah,
that's going to show up as wider with.
that's true. And that also depends on like how thick your gate dielectric was and so forth.
Right, so I wouldn't be convinced that but
No,
they're
you're right,
showing
you're
it as
right. Okay,
necessarily.
anyway, but I'm not trying to explain an experiment right now. I'm trying to do. You can tell me. I can guarantee from the beginning that it doesn't explain. Okay, good. So what happens when you turn on the displacement field for the dispersion relation of bilayer graphene? You start with 2 parabolic bands touching, and then as you turn on the displacement field, you try to push the conduction band through the valence band, There's an avoided crossing of this sort of thing. And what you get is this sort of Mexican hat shape with this perfect thing. Okay, again, I'm going to bring back trigonal warping later for everyone's the audience. But roughly what you do is you turn the conduction band, which used to be a parabola, into this Mexican hat shape. Okay, trigonal warping means that what happens is that this thing is not exactly a perfectly angularly symmetric dispersion. Has the dispersion breaks. This ring of minima breaks up into 3 discrete pockets. I'll bring it back later. Ignore it for now. Okay, so by the protocol I told you about before, if I want to think about Wigner crystals, I need to solve the single particle harmonic oscillator problem. I think about one electron sitting in the harmonic potential created by its neighbors. I solve for the ground state of the harmonic oscillator, and then I see is that on the right side of the limit. But now I have a different kind of harmonic oscillator. It looks like the normal harmonic oscillator, except the kinetic energy is not p squared. It's mod p minus p naught squared. So it's Mexican. So now the first question is, please go solve the harmonic oscillator with the kinetic energy that's Mexican nature. Okay, now I can't resist a very fun chapter of my graduate education, which was working not only Boris, but a very great nuclear theorist, high energy theorist, Misha Voloshin. And we would come to tea time every day in the Theoretical Physics Institute and chat with Misha, and he was a very smart guy. And I got stuck on a problem. We were trying to understand transport and bilayer graphene in the early days, and there was some mysterious feature we thought it was impurities. And I kept realizing there's a simpler and simpler problem I don't understand. For that reason, I didn't even understand the hydrogen atom. And the problem was sufficiently tricky that even Boris didn't understand it. So we knocked on Misha's door, and he more or less told me what to do in 30 seconds. And I'd come back and tell me what to do again in 30 seconds. So I'm very proud that this is Misha's one paper in PRB, and it was by virtue of me bothering him not. Anyway, the answer is that let me not go. We solved the problem of the hydrogen atom with convection atom dispersion. It was fun. It mapped onto the 1D hydrogen atom. And basically what happens is that your wave function wants to live near the ring of minima in the dispersion. So in momentum space, your wave function is going to look like some kind of ring. And now if you integrate out the radial degree of freedom, what you're left with is a 1D Schrodinger equation, and you can map it onto the problem of the 1D hydrogen atom. Okay, so we solved that. It was a lot of fun. And we found out later, as often happens, that the basic ideas had already been figured out in Russia 10 years earlier. Okay, so let me go back to this. The quick way to see what's happening here, I think, is just to replace R by I grad P, insert it back here, and rewrite things. And now what you're left with from the Hamiltonian is something that looks like a kinetic energy term instead of grad R, it's grad P squared, and a potential energy term that looks like P minus P naught squared. So the point is that you're left with a problem that looks like a normal particle rolling around a Mexican hat potential in real space. And then you say, what is the ground state of a particle in a Mexican hat potential in real space? Now the mass is something funny. And again, it looks like you do it, you get a wave function that looks like our ring in momentum space. Fourier transform, you get this funny thing that looks like a Bessel function modulated by a Gaussian in real space. But the funny thing is that the ground state energy is not H omega anymore, it's 1/2 H omega. So a 2D problem has effectively become a 1D problem. What does that mean? That the first quantum correction now is not H omega 1/2 H omega. It means that the first quantum corrections, the energy is somewhat reduced, and that means the Wigner crystal state is somewhat stabilized. So the existence of this Mexican hat dispersion relation makes the quantum mechanical kinetic energy a little bit reduced, gives the wave function this funny shape in real space, and the Wigner crystal state is a little bit stable. Okay, something much more interesting is about to happen. And that's when you realize that a ball rolling around in a Mexican hat potential has two kinds of excitations. It has the radial excitation that goes back and forth, that's kind of stiff, and it has a very soft angular excitation with the Goldstone mode. You can kick it in the angular direction for very low energy, arbitrarily low frequency. And what that means is that excitations to finite angular momentum are very cheap. So this is the ground state energy, 1/2 H omega. And then as you give it higher angular momentum L, energy goes up to L squared, but it's suppressed by this factor P naught. P naught's the radius of the Mexican. Okay, and this factor down here knows about the density. So in the limit where the Wigner lattice is very sparse, where the Mexican hat is very wide, excitations that finite angular momentum are very, very cheap. The lowest energy still has zero angular momentum, which you can excite the finite angular momentum very easily. All right, now it's time to bring in the role of barrier. Maybe you can anticipate what barrier curvature is going to do. It's going to couple angular momentum. Okay, so bilayer graphene, I think this we has already has two valleys, each valley with two pi variables. So in the absence of any displacement field, that 2 pi vary flux lives as like a delta function right at the k or k prime point. But now as you turn on the displacement field, the vary curvature sort of spreads out, and the ring of minima grows outward like this. And how do you couple that vary curvature? Let me just imagine that your electron is living in one of the two valleys of your k or k prime. How do you couple the vary curvature to the harmonic oscillator state? Well, it's by a kind of minimal substitution. Remember, vary curvature is like a magnetic field that lives in k space. So you do minimal substitution by replacing r with like r plus a instead of p with p minus a. So to do this, work through the details, and Sonia will tell you all the details at lunch if you want. And what you're left with is this quite nice result that says here's the energy as a function of the angular momentum L, but now instead of being L squared, it's L minus phi squared. And this phi is the flux of vary curvature to the interior of this ring. Okay, so the wave function is a skinny ring centered in some circle of radius k mod. Okay. But if there is more than pi vary flux to the interior of that ring, then the ground state is not L equals 0. The ground state is L equals 1. Okay. So the ingredients here are that the excitations to find the angular momentum would be very cheap to build Mexican net dispersion. Now couple those to vary curvature, you find that if the flux of vary curvature is greater than pi to the interior of that wave function, then the ground state is L equals 1. All right, so that's the basic idea. Now you go through and do the calculations using this sort of harmonic oscillator picture. And let me just sort of walk you through the phase diagram. So this is electron density. Sorry, these are theory units. Don't try to read real units off this. Talk about real units in a second. This is the displacement field. And what you're seeing is first, with no displacement field, there's no Wigner crystal state. So this Fermi liquid. Okay, I know there's lots of interesting stuff happening in what I call Fermi liquid. I'm just using Fermi liquid to mean everything that's not a Wigner crystal. It doesn't exist at t equals 0. You turn on the displacement field, you gap out the dielectric response, the Wigner crystal is allowed to exist. Now here you see this big prominence here. What's happening here is that at first the bottom of the band is just flattening, the electrons are becoming very heavy, Wigner crystal is really big, and then here is the point where you're sort of really making a well-formed Mexican net dispersion back down, reaching some finite density. Now the interesting thing that I just told you about is along the displacement field axis. This is the point right here. Sorry, ignore all these equations. This is the point right here where suddenly you have more than pi vary flux to the interior of the harmonic oscillator wave function, and you transition spontaneously from having a sort of non-magnetized Wigner crystal to having a Wigner crystal where each electron has spontaneous orbital magnetization. So if you could do the experiment and you could just sort of measure the magnetization as a function of displacement field to some density, you'd say, okay, here's a non-magnetized Wigner crystal. And then suddenly it jumps and you have a magnet. Okay, sorry, it's not literally non-magnetized right here because anytime you make the wave pack in momentum space with finite vary curvature, here you get some magnetization. But there's a discontinuous jump that's associated with L equals 0 to L equals 1. That's the big thing. Okay, now comes the sad part of my talk where I have to bring back trigonal warping, which I've been ignoring so far. I had this beautiful Manhattan dispersion so far that allowed for sort of almost free angular momentum modes. Now I have to remember that unfortunately graphene only has C6 symmetry, so I have to be C3 symmetry. So the ring of minima now becomes 3 discretes. Okay, so in a sense, I have around each point, this is his K point. My ring of minima breaks into 3 mini minimas with a small energy splitting or a small energy barrier. And now you ask, is there something like a magnetization transition possible for this problem? And you say, well, actually, this starts to look, what's going to happen at low energies, the electron will reside in some combination of the 3 valleys, some combination of these 3 mini valleys. And then I ask, would it like to live in a symmetric combination of the 3 mini valleys or some combination that sort of winds? And that looks like the momentum space version of this mildly famous problem of a particle hopping on a triangle in a magnetic field. So you just have a triangle, a particle moves on 3 sites, hops among 3 sites. And the ground state is for it to live in a symmetric combination of 3. And now as you turn up magnetic field, if there's enough flux to the interior of that triangle, then it will spontaneously go into a winding state. The ground state and the first excited state will. So in principle, the same thing happens here, and it looks like we can rescue the same magnetization transition in the Wigner crystal state. Unfortunately, there's a problem, which is that the hopping, the effective hopping or the tunneling amplitude for an electron flow from this mini valley to this one is exponentially small deep in the Wigner crystal phase. Deep in the Wigner crystal phase, the wave function is a very small little, lives very near the bottom of this pocket here, and there's some tunneling action to go from one mini valley to the other. Yeah, sorry.
Can you, if you increase temperature, can you somehow make this happen before it melts or something like that?
Okay, we tried playing with it, nothing worked, but I will come to something interesting. Anyway, unfortunately, what happens is that the splitting in energy between the symmetric combination, the symmetric state and the winding state is very small. It's exponentially small deep in the Wigner crystal state, which means things that are outside of the description I've been using so far can easily overwhelm it. And what's outside of the description is the fact that I've been assuming that the potential well this thing sits in is radially symmetric. It's not actually radially symmetric, it only has the same symmetry as the Wigner lattice. So that confining potential actually is kind of clamshell shape. It has like a C6 modulation to it. And that C6 modulation can pick up a particular superposition of the 3 mini valleys over something that winds or sits symmetrically. And actually, there's this nice paper coming out of, this is Vladimir Tavera's PhD work in Steve Gilson's group, pointing out that if you have sort of three mini valleys or 3 pockets, you generically end up with some non-trivial ordering of non-trivial mini valley ordering in real space. So this is the real space Wigner lattice that you're seeing, and there's some pattern of an electron sitting in this valley and this one, this mini valley. So it looks like the ground state is instead going to be like this, but there's still a few interesting things. So unfortunately, this beautiful Mexican hat physics seems to be out the window, but there are some kind of interesting things that can still happen to the Wigner crystal state in bilayer graphing, and I'll just mention a couple of them. One is that the nature of these mini valleys sort of changes with displacement. At small displacement field, I don't know how easy it is to see, the mini valleys are sort of elongated this way. And at large displacement field, they become elongated in the opposite direction. So what that means in terms of the spatial patterning of their ordering is that as you increase displacement field, you flop from one ordering pattern to another at a critical value of displacement. So at low displacement field, the optimal ordering will be this, and then at larger than critical displacement field, they'll flop to a different ordering pattern because the sort of shape of the mini valley switch. So that might mean that right near that critical displacement field, the system is sort of degenerate between these 2 ordering patterns, and then you could have a large entropy and you get something like a Pomerantz effect, where you turn up the temperature and it stabilizes the Wigner crystal phase because the Wigner crystal has an unusual amount of entropy right near that special. But it seems possible. Okay, another interesting thing that I haven't talked about actually is that, in fact, bilayer graphene, if you properly think about trigonal warping, has not 3 mini valleys, but 4. There's a central one right in the middle. So there are these 3 ones, and there's another one. And as you turn on the displacement field, this central one disappears. Okay, so it starts with sort of 4 Dirac points all clustered around the K point. And then as you turn on the displacement field, they all gap out, but the central pocket gaps out the quickest and then inverts and becomes a maximum. So as you're at not too high displacement field, what you see is that there are sort of lighter side pockets and a shallow, heavy central pocket. And at low displacement field and low density, the Wigner crystal is sort of, or the electrons in the Wigner crystal are unclear whether they want to live in the side pocket or in the central pocket. There's kind of competition. This one provides a lower potential energy, and this one provides a lower energy, or a lower. So you can again, or you can tell Sandeep to work out the phase diagram, and that's for you. Displacement field versus electron density, and you have this funny sort of bimodal picture where there's something that lives primarily in the central pocket, something that lives primarily in the side pocket. And it leads to all sorts of funny things, like if you're at here, which is a pretty realistic value displacement field actually, and you ramp up the electron density, you'll find that the Wigner crystal will first crystallize here in the side pocket at very low density down here, then melt, then crystallize again in the central pocket and melt again. So you get this kind of double re-entrance of the Wigner crystal phase, solid, liquid as a function of density. I haven't heard that before. It seems possible in principle. Unfortunately, the limit of what is so far realizable in density ends about here. So, you have to make a very clean sample to see pulse transitions, but it seems to be possible.
This is from Lindemann, it just.
Yeah, this is just Lindemann criterion with a single particle. Okay, that's pretty much all I have to say. I mean, the thing that is kind of exciting is that it looks like Berry curvature can create a new kind of Wigner crystal phase that has this spontaneous orbital magnetization, and there's a sharp transition associated with it. Unfortunately, in real bilayer graphene, that seems to be ruined by trivial warping, but it's replaced with this sort of interesting non-trivial patterning of mini valley ordering that we do interesting things on its own. And with that, I'll stop and take questions.
Can I have liquid, please?
Liquid Wigner crystal. That sounds like not a Wigner crystal, but some pneumatic state, something like that. Maybe. Maybe. I mean, and often these things are limited by your imagination, what states you're thinking about.
All right. Questions, please.
Anton.
So this is within one valley, Cape Point, right?
Yeah, sorry, I'm
Near
assuming.
Cape Prime, actually, where is time reversal?
Yeah, thank you, sorry. So, there's one sign of Berry curvature at K and the opposite sign at K prime. So probably what I didn't state explicitly is that I'm sort of already assuming that the system has valley polarized into one valley or the other, and that would happen by exchange interaction, paramagnetic. So, we did our best to estimate like what's the magnitude of the exchange, what temperature we have to go to see. So valley is like an Eisen variable. So it'll in general be polarized, certainly deep in the crystal phase. And then you ask how low in temperature will have to go with valley polarized. Kind of a question. You can do the direct calculation of estimating the exchange interval between two electrons in a Wigner lattice. But really the dominant exchange process can be some complicated ring exchange. So I can only give you a lower bound estimate for where the ordering. But yeah, I'm assuming the interactions are valuable, at least if you want to macroscopic magnetization.
Right?
What will happen if we turn on the magnetic field? That's how that will turn into the lambda level physics.
To be honest, even without Berry curvature, in the most vanilla scenario, it's hard to understand what happens to a Wigner crystal at strong magnetic field. How does it turn into quantum Hall physics? We should talk about it offline. There are interesting experiments that show you can turn a Wigner crystal into an integer quantum Hall state by a large magnetic field. It can't be understood within the simple, harmonic oscillator equation that I gave you. So
No, you need mixture of Landau levels for this.
yeah.
Landau levels should be destroyed and mixed.
Anyway, as far as I can tell, it's not a completely settled question even in the most conventional setting.
Have you thought about the Phonon density of states of the Wigner crystal?
We're thinking about that right now and have nothing, or at least I personally, maybe Sandy knows. We're thinking right now, well, what are the Phonon modes of a Wigner crystal with Berry curvature?
And what does it do when it gets close to melt? Does it soften or does it?
That's you.
Yeah, okay, I don't know. Short answer is I don't know. I remember you had these experiments that showed the Phonon modes of the Wigner crystal seemingly stiffening when you came next to melting, and I never understood why. To me, it seemed like they should soften. So I don't have an answer. I would expect them to soften, but
First voice, then Aviram.
Probably need something. Small density exchange energy is small.
Yeah.
It doesn't favor separation between the imbalance, valley imbalance, right?
sorry. At small density, the exchange interaction is very small, so you'd have to put a very, very small temperature in order to see valley polarization.
Do you? No, I'm saying that there will be no Even
Are you
at
talking
zero
about- are you
temperature.
asking a statement about literally zero temperature?
Yes.
I think at very small density, the interaction is still ferromagnetic. It's just very, very weak. It's exponentially weak.
Okay, very formulate because it's not the question. So which parameter allows you first to claim that there is value polarization and then do Wigner
Yes,
crystal?
okay, good.
Is one way. Is there any parameter or it's a belief or what is the status of?
I mean, the only parameter here is RS, and my claim is that very large RS. So, okay, but imagine there's no value degree of freedom, just spin degree. Right? I think it's settled that at deep in the Wigner crystal phase, the interaction between two electrons in the Wigner crystal is ferromagnetic in terms of real spin.
Yeah.
So, okay, in a sense, if you want to ask, does the valley be the same
depends
real
on-
spin? That's it.
Depends on lattice, right?
Okay, you're okay. So far, I guess it's a statement of belief.
Okay.
But I see no reason why it wouldn't also be ferromagnetic, but it's.
So to say that another way, why couldn't an individual localized electron, your localization length is much more than the lattice constant.
You mean the literal lattice constant of stuff?
Yeah.
Yeah,
It could be mixed valley, I guess, right?
sure, yeah.
That's a possibility that,
Yeah, okay, so you're saying why wouldn't it
Yeah.
prefer to live in some superposition of the two values
Yeah.
rather than polarizing them together? Yeah, I don't have a strong answer.
Just a naive question. So if we're not in the Wigner crystal regime, but we still have the Berry curvature, then when we dope electrons, we do expect to see magnetization going up smoothly. But I guess in the Wigner crystal regime, it's off and then on abruptly. Is that correct?
Okay, sorry, let me back up. I think you're talking about this
Yeah.
picture here.
Yeah.
Yeah.
Okay.
So, right, so as you add electrons to a band with Berry curvature, you generally produce magnetization. And that's the same thing happens here. And in this particular setting, which is not a realistic description of bilayer reaction, I suppose, there's a jump that's associated with this extra orbital magnetization. But yeah, I mean, generically, anytime you fill a band with Berry curvature, it's a smooth evolution of the magnetization, the same thing happens.
All right, let's bring Brian. We have reception starting in 15 minutes from now. Tamara building.
Oh, that is.
Next year, that's your. That's I find your.
Exactly.
This right there.
Oh, yeah, I know.
this is you.
Looks like you go.
You can walk with me if you want, it's like alumni building.
So someone wants.
Or yeah, after the day it's fine. Yeah. Okay.
You wake up to